This question is about gases. The question says, a number of assumptions are made when explaining the behavior of a gas using the molecular kinetic theory model. The first part of the question says, state one assumption about the size of molecules. These assumptions can be remembered using the mnemonic device VINCE, where each letter stands for a different assumption. V stands for the fact that the volume of the container is much larger than the volume of all the gas molecules. I stands for that the intermolecular forces between the gas molecules are negligible, except during collisions. N stands for the fact that the number of gas molecules that we're talking about is very large. C stands for the fact that the time between collisions between gas molecules is much larger than the time taken to do a collision. And finally, E stands for the fact that all collisions between the gas molecules and the container are elastic. Therefore, the assumption that concerns the size of the gas molecules is V, which says that the volume of the gas molecules is negligible compared with the volume of the container. So that's our answer for this part of the question. The next part of the question says, Figure 1 shows how the pressure changes with volume for a fixed mass of an ideal gas. At A, down here, the temperature of the gas is 27 degrees Celsius. The gas then undergoes two changes, one from A to B, like so, and then one from B to C, like so. Because they're going to be useful later, I'm going to mark on the coordinates of A, B, and C on this graph. So A is at 0.7 times 10 to the minus 3, and then a pressure of 10 to the 5. B is at a volume of 0.5 times 10 to the minus 3, and then a pressure of 10 to the 5. And then C is at a volume of 0.3 times 10 to the minus 3 meters cubed, and a pressure of 2 times 10 to the 5 pascals. The next part of the question then says, calculate the number of gas molecules trapped in the cylinder using information from the initial situation at A. To do this question, we first note the quantities that we've been given that correspond to the gas at A. Firstly, we've been given its temperature, and that's 27 degrees Celsius. We've also got the position of A on a pressure-volume diagram, so we also have the pressure and the volume, as PA is 10 to the 5 pascals, and the volume at A, VA, is given by 0.7 times 10 to the minus 3 meters cubed. We then need an equation that relates TA, PA, and VA to the number of gas molecules, big N. To do this, we can use the ideal gas equation, which says that for an ideal gas, the pressure multiplied by the volume is equal to N kBT, where P is the gas's pressure, V is its volume, T is its temperature, and big N is the number of particles. So using this, we can rearrange N is equal to PV divided by kBT by dividing both sides by kB and T. We then substitute values in for T, PA, and VA. So the number of gas molecules is given by 10 to the 5 multiplied by 0.7 times 10 to the minus 3, and make sure to include the units when you do this. So include that 10 to the minus 3 that was noted in the volume axis. On the bottom, we have the value of Boltzmann's constant, which is a constant given to us in the data sheet, which is about 1.38 times 10 to the minus 23. And then we need to include the temperature. Now, the temperature is given as 27 degrees Celsius. However, whenever we do these thermodynamic calculations, we need to convert the temperature into Kelvin first. Therefore, what we need to do is TA in Kelvin is 27 plus the conversion plus what you need to convert to Kelvin, which is to add 273, because every temperature in Celsius is equal to the temperature in Kelvin minus 273. So if I want to convert back to Kelvin, then I need to add 273 to it. So that's 300 Kelvin. So then I need to make sure to use the temperature in Kelvin in my calculation, like so. And so when I've done that, I can calculate the value of N, and I get about 1.691 times 10 to the 22, which is about what we expect. We expect the number of gas molecules to be similar, around the same amount as Avogadro's number, which is 6.02 times 10 to the 23. Therefore, this isn't too bad and too far away. Then, because the data in the question is given to two significant figures, we can give our answer as 1.7 times 10 to the 22 gas molecules. In this question, we get 1 mark for successfully converting TA, the temperature at A, into Kelvin, and then for using it in an equation in an attempt to find N. So 300 will get us our first mark, and our second mark is for a correct numerical answer, 1.7 times 10 to the 22. The next part of the question says, calculate in Kelvin the change in temperature, so the change in temperature of the gas during the compression that occurs between A and B. In order to do this question, we need to use the ideal gas law again. In this case, what we can say for an ideal gas is that if P times V is equal to N kBT, then if we divide both sides by T, then we're left with PV over T is equal to N times kB. Now, the question told us that we had a fixed mass of gas. So what that means is that we have the same number of gas molecules at all times, and therefore N is always the same. So N is a constant. What that means then is that I can write an equation that says that the pressure times the volume divided by the temperature at any time before a change is equal to the pressure times the volume divided by the temperature after the change. In other words, if I give quantities at A a subscript A and quantities at B a subscript B, then I have PA VA divided by TA is equal to N kB, which is a constant because this is a constant number of gas molecules multiplied by Boltzmann's constant, kB, which is a constant, which is equal to PB times VB divided by TB. So therefore, I can extract information about the temperature at B using just the pressure at B, the volume at B, and the other quantities that I know. So now we can rearrange this equation, firstly by multiplying both sides by TB and dividing by PA times VA to get TB divided by TA is equal to PB times VB divided by PA times by VA. Then we multiply both sides by TA to get TB is equal to PB times VB over PA times VA times TA. Okay, so at this point we need to remember what the pressure and volumes at A and B are. So we can do this by referring to our graph. If we look at our graph, we can see that the volume at A is 0.7 times 10 to the minus 3, the volume at meters cubed. The volume at B is 0.5 times 10 to the minus 3 meters cubed, and they both have the same pressure. Therefore, in this question, we could say that PA is equal to PV, PB. So what that means is that in this equation, these two cancel. So we're left with TB is equal to VB over VA times by TA. So then we can substitute in numbers for this, and we have that VB is equal to 0.5 times 10 to the minus 3, and VA is equal to 0.7 times 10 to the minus 3. And that's multiplied by the temperature at A, which, as we worked out in an earlier part of the question, was 300 Kelvin. So we have to keep using Kelvin here. So then we can do this calculation, and we find that TB is equal to 214.285 ... Just a quick note on this, which is that we didn't need to include the 10 to the minus 3's in this case, because we were taking the ratio of the two volumes and they were already in the same units. Therefore, we can see that these 10 to the minus 3's just cancelled. We could save ourselves a bit of work by not inputting this, in the exact same way that we decided not to include PA and PB because they were the same value already. The 10 to the minus 3's will just cancel each other out. Okay, so the final part of this question is to get the change in temperature. So we need to calculate TB minus TA. Which gives us an answer of 300 minus 214.285 ... which is equal to approximately minus 86 Kelvin. Therefore, the change in temperature is about minus 86 Kelvin to two significant figures, since that's the degree of precision given for the data in the question. In this question, we got 1 mark for correctly calculating the temperature at B, 214, and then we got our second mark for calculating the change in temperature, TB minus TA, as minus 86 Kelvin. The next part of the question says, deduce whether the temperature of the gas changes during compression from B to C. In order to do this question, it is helpful to consider what defines an isothermal change, so isothermal being the same temperature. So what we want to determine is whether the change B to C is isothermal. To do this, we consider the ideal gas equation again, which says that PV is equal to NkBT. Now, if T is constant, i.e. if the change is all at the same temperature, so the temperature before is the same as the temperature after, then what it means is that the number of molecules of the gas times by the Boltzmann's constant times by T also has to be a constant, because N is constant too. Therefore, in an isothermal change, what we have is that PB, or P before, times V before, or PV VB in this case, is equal to PC times by VC. So our strategy is going to be to calculate PB VB and PC VC and see if they're the same. If not, then the change is not at the same temperature because it's not isothermal. Doing this then, we can read off data from the graph, like so, specifically that the volume at B is 0.5 times 10 to the minus 3, the volume at C is 0.3 times 10 to the minus 3, and these are both in meters cubed. The pressure at B is 10 to the 5 pascals. The pressure at C, that should say 2.05 times 10 to the 5. So if you look carefully, it's 2.05 times 10 to the 5 pascals is the pressure at C. So then we can calculate PB times VB and PC times VC. Doing this then, PB times VB is equal to 10 to the 5 pascals multiplied by 0.5 times 10 to the minus 3 meters cubed, which gets 50 Pascal meters cubed. And note here that the unit isn't joules, because we're not talking about energies here. We can do the same for PC times VC. as being equal to 2.05 times 10 to the 5 times by 0.3 times 10 to the minus 3, and that's equal to 61 Pascal meters cubed. So what we can see is that PB times VB is not equal to PC times by VC. So the temperature of the gas must change because the change is not isothermal. Since the change is not isothermal. Okay, so in this question, we get 1 mark for calculating PB times VB and PC times VC. And we get 1 mark for our comment that they're not equal since the change isn't isothermal. Note that since PC times VC is higher than PB times VB, what that means is that since P times V is proportional to T, since N is constant, like we were talking about, what it means is that the temperature has actually increased as the gas has been compressed from B to C. This is due to the work done on the gas, which is the subject of the next part of the question. The next part of the question says, compare the work done on the gas during the change from A to B with that from B to C on figure 1. So to do this question, what we need to know is that the work done on the gas is the area under the PV graph. So what that means then is that if we can calculate the area under the PV graph between each of the changes A to B and B to C, then we can figure out how the work done compares between the two. Drawing a quick sketch of our graph, it looks like the following. So if this is V and this is P, then we have a straight line part, this is A to B, and then another part up to C, like that. So what we're going to do is we're going to calculate the area under this graph for each of the changes A to B, so this area, and B to C, this area. There are multiple ways we could do this calculation. Either we could count the squares, which is slow but reliable, or we could break up the area into a number of simple shapes that we know how to calculate the area of. In this case, what we're going to do is we're going to subdivide the areas like so. So on our graph, we have B, C, A. We're going to calculate the area of this like a rectangle. We're then going to subdivide this bit into another rectangle, which will have the same height the whole way through, and therefore we can just calculate the area of, and we'll count the squares under this bit. Okay, so to do that then, we need the values of the pressure and the volume at A, B, and C. So those can be read off earlier in the question, but essentially if I have A, B, and C, and then I have volume, and then I have pressure, and the volume's in 10 to the minus 3 meters cubed, the pressure's in 10 to the 5 pascals. Then I have the A has 0.7 here, and has 1 as its pressure in units of 10 to the 5 pascals. B has 0.5 here and also has 1 in units of 10 to the 5 pascals, and C has a volume of 0.3 times 10 to the minus 3 meters cubed and has a pressure of 2.05 times 10 to the 5 pascals. So our first mark is for saying work done is area under the graph. And for calculating the area between A and B, so doing that, this rectangle has a height of 1 times 10 to the 5 pascals, or 10 to the 5 pascals, because it's just this. It has a length of 0.7 minus 0.5 times 10 to the minus 3 meters cubed, where I'm going to keep that out of the diagram to prevent it from getting too cluttered. So this V is in 10 to the minus 3 meters cubed. So we have that this is equal to 0.7 minus 0.5 times 10 to the minus 3 is equal to 0.2 times 10 to the minus 3 meters cubed. So the area is equal to 10 to the 5 multiplied by 0.2 times 10 to the minus 3. And that gives us 20 joules. Now we do the same for B to C. So for the rectangle, we have the same height. It's 10 to the 5 because it's just the height of B. The width is the same as well because the change in volume is the same. So in other words, the length of this rectangle is 0.5 minus 0.3 times 10 to the minus 3, which is equal to 0.2 times 10 to the minus 3 meters cubed. So therefore, the area under rectangle, or the area of the rectangle, still gives us 20 joules as well. Now finally, for the bit between C and B that's not taken into account by the rectangle, what we need to do is we need to count squares. So we go up to our graph, we subdivide off the bit that's not part of the rectangle, and then we attempt to count squares. So in order to proceed, we need to know what the area of one square is, because that will tell us how much work done corresponds to one square. We then need to find the total number of squares and multiply these two together. So the area of one square, so one subdivision on the volume, like so, is given by 0.01 times 10 to the minus 3 meters cubed, and one subdivision in the pressure axis is given by 0.05 times 10 to the 5 pascals. So multiplying these two together, you get a value of 0.05 joules corresponds to an area of one square. If you count the squares in this section here, which I won't do on video, then you get approximately 170 squares. Therefore, the area between the rectangle and curve B to C is just given by 0.05 multiplied by 170, which gets you 8.5 joules. So Now we need to compare the work. So work done from B to C overall is equal to 20 plus 8.5, which is equal to 28.5 joules. So the work done from B to C is greater than the work done from A to B by 8.5 joules. In this question, we got 1 mark for calculating the work done between A and B, as 20 joules, and the second mark for an attempt to calculate the area, the work done between B and C. Our final mark is for saying that the additional work done from B to C compared to from A to B is 8.5 joules. This question is about magnetic fields. The question says, Figure 2 shows 2 magnets supported on a yoke placed on an electronic balance. And that's what we see in the diagram, the magnets and the yoke. The magnets produce a uniform horizontal magnetic field in the region between them. A copper wire, DE, is connected in the circuit shown in Figure 2, like so, and is clamped horizontally at right angles to the magnetic field. The next part of the question says, Figure 3 shows a simplified plan view of the copper wire and magnets, and we can see the magnets marked on as well as the wire itself, looking down from above. When the apparatus is assembled with the switch open, the reading on the electronic balance is set to 0.000 grams. This reading changes to a positive value when the switch is closed. The first part of the question then says, which of the following correctly describes the direction of the force acting upon the wire DE due to the magnetic field when the switch is closed? And it wants us to pick the correct option. Before we can answer this question, we need to think about the situation that we've got in this question. Returning to the diagram above, what we can see is that we have the wire connected between the 2 magnets that are on the yoke. The wire isn't physically connected to the yoke itself, and so isn't physically pushing on the balance. Therefore, things are a little bit more complicated than they look at first. To make progress then, we should think about how the balance does experience a force. The wire isn't connected to it, but the yoke is. The yoke is sitting on top of the balance. Now, as mentioned earlier in the question, whenever the switch is open, the reading on the balance is 0 grams. It means that whenever the switch is closed, the extra force acting on the balance has had to increase, because the balance registers the force pressing down upon it. Therefore, it means that the yoke is applying extra force. Force downwards onto the balance. At this point, we should also note that the wire must feel a force. Since it's a current within a magnetic field. Then we need to think about which objects are interacting. Specifically, the magnets and the yoke are interacting with the copper wire. Then, since the copper wire feels a force, the yoke must also feel an equal but opposite force due to Newton's third law. This means that whatever force the yoke feels, the wire is feeling the opposite and equal force as well. So as a result, if the yoke is being pushed downwards due to interacting with the copper wire, then the copper wire must have a force on it that wants to pull it outwards to satisfy Newton's third law. Therefore, our answer is vertically up. The next part of the question says, label the poles of the magnets by putting north or south on each of the two dashed lines in figure 3. And figure 3 was the plan view of the diagram of the magnets. In order to do this, we need to use Fleming's left-hand rule, which says that if I have 3 different quantities, the force, the magnetic field, and a current, they will be aligned at right angles to each other in this arrangement. So in this case, we need to orient the force in the direction that we actually see it. Specifically, we know that the force is coming out of the plane of the paper because the wire wants to move vertically up, and this is a plan view. So this little arrow here represents the direction of the force. This like arrowhead represents the force coming out of the plane of the paper. Now, using Fleming's left-hand rule, then we can also say what we know the current is. Now, because the battery is connected going from E to D as positive to negative, we know the current is flowing from E to D. So the current is flowing this way. So current. Then what we can say is, by using Fleming's left-hand rule, if the force is going upwards and the current is going from E to D, then the magnetic field must be going from right to left. So in this case, we have field here. So therefore, what we need is to have the North Pole on the right-hand side and the South Pole on the left-hand side, because the field lines always go from the North Pole to the South Pole, like so. The next part of the question says, define the Tesla. The Tesla is the unit of the magnetic flux density, which appears in the equation F, the magnetic force acting on a wire, is equal to the magnetic flux density B multiplied by the current I through that wire multiplied by the length of the wire inside the magnetic field. So inside the magnetic flux density. Now our definition of the Tesla says that we get a 1 Newton force whenever I have 1 Tesla of magnetic flux density, 1 amp of current in the magnetic flux density over a length of 1 meter of that wire inside the magnetic flux density. So our definition of the Tesla is the magnetic flux density for which a wire of length 1 meter carrying a current of 1 amp experiences a force of 1 Newton when the current is perpendicular to the field. Note that this comment about the current being perpendicular to the field, which you didn't have to say to get the mark, but is still important, comes from the fact that the full equation is equal to F is equal to BIL sine of theta degrees, where theta is the angle between the current and the field. Therefore, if the two aren't at 90 degrees, so sine of 90 degrees is equal to 1, then this force will decrease, because for smaller angles between them, sine theta decreases. Therefore, you get the maximum force when the field and the current are perpendicular, and this is incorporated into the definition of the Tesla. The final part of the question says, The magnets are 5.00 centimeters long, when the current in the wire is 3.43 amps. The reading on the electronic balance is 0.620 grams. Assume the field is uniform and 0 beyond the length of the magnets. Calculate the magnetic flux density between the magnets. So to answer this question, we're looking to find the magnetic flux density, and we know indirectly what the force is from the electronic balance, and we know the current in the wire as well as its length. The reason we know the length is because the length of the wire inside the magnets is all that we care about. We've been told that the magnets are 5.00 centimeters long, so this is our length of wire that's between the magnets. The reason we don't have to consider any length of wire that's even slightly outside the magnet is because we've been told that the field is 0 beyond the length of the magnets. We also know the current in the wire, like so. So then we can use the equation F, the force acting upon the wire, is equal to B times I times L times sine theta. We know that theta is 90 degrees because we know that the field and the current are perpendicular to each other. Therefore, sine theta is equal to 1, as we discussed earlier in the question. Therefore, we can simplify to F is equal to BIL. From here, we can rearrange this equation for B. So we have that B is equal to F divided by I times L. At this point, we need to determine what F is. To do so, we need to use what we know about the reading on the electronic balance. Specifically, we know that our balance gives you the mass of whatever object is placed upon it. It gets this mass from doing a calculation from the force. Specifically, it takes the force that it receives, which is what it actually reads, and divides by the acceleration due to gravity, g, to get a mass. Therefore, if we multiply the reading on the balance by g, then we'll get the force it experiences. So, force received by balance F is equal to 0.620 times by 10 to the minus 3. This is to convert grams into kilograms. And then multiplied by the value of g, 9.81. Therefore, since we know that the force exerted on the balance is the same in magnitude as the force exerted on the wire, we can plug this value of F into our expression for B as 0.620 times by 10 to the minus 3 times by 9.81 multiplied by or divided by the current, which is 3.43 amps, multiplied by the length, 0.05 meters, which is 5 centimeters times 10 to the minus 2. So doing that calculation, we find that B is about 0.035467, so on, which, to the degree of precision of data given in the question, which is 3 significant figures, because all pieces of data are given to 3 significant figures here, we have 0.0355 Teslas. In this question, we got 1 mark for the correct formulation of an equation involving B is equal to F divided by IL, with F is equal to the mass recorded by the balance multiplied by G. And the 2nd mark for doing that substitution correctly and getting the correct final answer. This question is about magnetic fields. The question says, a cyclotron has 2 D-shaped regions where the magnetic flux density is constant. The D-shaped regions are separated by a small gap. An alternating electric field between the D-shaped regions accelerates charged particles. The magnetic field causes charged particles to follow a circular path. Figure 4 shows the path followed by a proton that starts from O, near the center of the cyclotron. So what we see is the proton starting from O. It's in the region of the electric field when it's outside the two D-shaped regions. Therefore, it accelerates towards one of the Ds, like so. In the D region, it takes a circular path, which will bring it back out of one D region and into the gap between the two, where it will be accelerated by the electric field again before going into the second D-shaped region, following a circular path, and so on. The first part of the question then says, explain why it is not possible for the magnetic field to alter the speed of a proton while it is in one of the D-shaped regions. In order to answer this question, we need to consider the forces acting upon the proton. If we draw a force diagram for these forces, then we find that we have the proton, and now consider it, say, at this point here, point 1. So this is at 1. Then we have the velocity going directly to the left, and we have the force, which we can work out from Fleming's left-hand rule, as going downwards. So to see this, you can use the fact that a proton is a current. We have the flux into the plane of the paper. So that's the flux. And then that causes there to be a force going downwards. And you can verify this by using Fleming's left-hand rule. Note that the proton moving in the direction of its current, in the direction of its velocity, constitutes a current because it is a moving charge. If we had an electron, the current would be going in the opposite direction since the charge of the electron is negative. Anyway, what we see from considering this is that the force is at right angles to the velocity. And in fact, from Fleming's left-hand rule, what we can see is that the force is always at right angles to the current. Therefore, what we realize then is that because the force is always at right angles to the velocity, the force is never acting in the direction of motion of the proton. Now consider what would have to happen for the speed of the proton to change. For the speed to change, we would need to change the kinetic energy, which is given by the formula 1/2 times m times v squared. So this would have to change too. But we know that to change the kinetic energy, we must do work. The definition of doing work on something is to say that you apply a force over a distance. And this force must be in the direction that the object moves, or must have a component going in the direction that the object moves. But since the force is always perpendicular to the velocity, the force does not have a component along the direction that the proton moves, and therefore no work can be done, so no kinetic energy can be changed, so the speed can't change either. So our answer to this part of the question is that the magnetic force is perpendicular to the velocity. Therefore, the force never acts in the direction of motion of the proton. Therefore, it can do no work on the proton and thus cannot change its speed. The next part of the question says, derive an expression to show the time taken by a proton to travel around one semicircular path is independent of the radius of the path. To do this, we need to collect together what we know about the motion of the proton. Specifically, we know that it is moving under a magnetic field, or a magnetic flux density. So this means that we can use the equation F is equal to B times Q times V sine theta, if Q is equal to E, because this is a proton and it has a charge of 1 times the elementary charge. We also know that its circular motion So we can use equations like F is equal to mv squared over r. V, the speed, is equal to the angular speed times by the radius. And we can also use that the angular speed is equal to the angle that you move through divided by the time taken to move through that angle. So these are the equations for the centripetal force, the force being equal to the mass times by the speed squared divided by the radius. And I've talked about these two already. We could also use other circular motion equations, but these are going to be the main ones. And I'll explain why we picked them in a second. Note that in the equation for the magnetic force, we have a sine of theta, where theta is the angle between the current and the field. Since the field is always going into the plane of the paper, and the velocity is in the plane of the paper, these two are perpendicular, so theta is equal to 90 degrees. So we're just left with F is B, E, V, where B is the magnetic flux density, like I said, E is the elementary charge, and V is the velocity of the proton. Or rather, the magnitude of the velocity of the proton. In other words, its speed. So in order to proceed, we're going to need an equation for T, and this equation is going to have to incorporate the fact that we're undergoing magnetic motion. So in order to do that then, let's first incorporate the fact we have magnetic motion by using the equations for F. So circular motion plus under magnetic field. So we chose this because we wanted to incorporate the fact that we have the magnetic flux density B. So we can use that B EV is equal to mv squared divided by r. So the bit on the left comes from the motion under a magnetic field, and the bit on the right comes from the centripetal force. So rearranging this a bit, we can multiply both sides by r and divide both sides by v. So we're left with v, and then divide both sides by m as well. So we're left with v is equal to b e r divided by m, like so. Now we want to relate v to the time taken to go around one semicircular path. So to do that, we use the fact that v is equal to omega r, because this is just the angular speed multiplied by the radius, and our angular speed, omega, is given by pi divided by t. So this is the time taken to go around a semicircular path. So this is just saying that it took me a certain amount of time to move through an angle of pi, since an angle of pi constitutes travelling halfway around the circle, as 2 pi radians makes up a full circle. Note that for all of the circular motion equations, we have to use angles in radians, not in degrees. From there, what we do is we can substitute this into our equation for v, so we get a second equation for v, as v is equal to pi r divided by t. We did this because we want to have two equations that are equal to v so that we can set them equal to each other and hopefully eliminate r. So then we combine these two equations together, and what we have is that b times e times r divided by m is equal to pi r divided by t. Tidying this up a bit, we end up with an equation that looks like t is equal to pi m divided by be. So what we've done is we've divided both sides by r because it cancels out. Then we've multiplied both sides by m and divided both sides by be. And then finally, just to round things off, we need to say that this is independent of r. In this question, we got 1 mark for using the fact that the centripetal force is equal to the magnetic force, so this equation here. We got a 2nd mark for our second equation that related v to the time and the radius, so v is pi r divided by t. And we got our third mark for forming our equation for t and stating that this is independent of r. The last part of the question says, the maximum radius of the path followed by the proton is 0.55 meters, and the magnetic flux density of the uniform field is 0.44 teslas. They tell us to ignore any relativistic effects, which would make this question more complicated. It then says, calculate the maximum speed of a proton when it leaves the cyclotron. So in this question, we've been given the radius and we've been given the magnetic flux density. Note that we know the mass of the proton. So now what we need to do is we need an equation which relates the maximum radius and the magnetic flux density to other things we know and the maximum speed of the proton. From the previous part of the question, we have an equation that relates v, the speed, to these quantities in terms of things we know. So v is the magnetic flux density, r is the radius, e is the charge of the proton, and m is its mass, which are all things we know. Therefore, what we want to do is use this equation, v is equal to b e r divided by m. So from there, what we need to note is that the maximum speed is at the maximum radius. This is because the radius is directly proportional to the velocity as we see from, or directly proportional to the speed as we see from this equation. So v directly proportional to r. Therefore, we can calculate the maximum speed just using the numbers given in the question. In other words, v is equal to 0.44 magnetic flux density multiplied by the elementary charge, 1.60 times 10 to the minus 19, times by the maximum radius, 0.55, divided by the mass of the proton, which is 1.673 times 10 to the minus 27. This is the proton mass. Therefore, we're left with v is equal to 2.3144 times 10 to the 7 meters, which is approximately 2.3 times 10 to the 7. So our answer is 2.3 times 10 to the 7 meters per second to two significant figures, since this is the degree of precision for the data given in the question. In this question, we got 1 mark for the correct rearrangement of this equation for v and for an attempt to substitute in the numbers for v, and we get our 2nd mark for a correct final answer. So this question is about nuclear reactors and fission. The question says, the core of a thermal nuclear reactor contains a number of components that are exposed to moving neutrons. The first part of the question then says, state what happens to a neutron that is incident on the moderator. So the purpose of the moderator is to take the fast-moving neutrons that are produced by fission and slow them down. If they are not slowed down, the fast-moving neutrons cannot be absorbed by more atoms of the nuclear fuel, and thus fission cannot continue. Therefore, the moderator allows the reaction to continue. The slowing down happens from collisions of the neutrons with atoms in the moderator, which are elastic. Therefore, the answer is that the neutron collides with atoms in the moderator and loses speed as it is slowed down by the collision. The next part of the question says, state what happens to a neutron that is incident on a control rod. The purpose of the control rods in the nuclear reactor is to control the rate of reaction. It does this by absorbing neutrons. The reason this is important is because each fission reaction produces more than one neutron, so that if fission reactions were to continue unchecked, the number of fission reactions that happen every second would increase very quickly. If some of these neutrons are, however, absorbed by the control rods, then what it means is that less neutrons are available to react, so the reaction can be sustained at whatever rate is required. Therefore, our answer here is that the neutron is absorbed. The next part of the question says, a slow-moving neutron is in collision with the nucleus of an atom of the fuel which causes fission. Describe what happens in the process. So in this reaction, what I have is a neutron, 10N, colliding with the nucleus of uranium-235. Then, what happens is the uranium absorbs the neutron to form a different version of uranium, uranium-236, and this quickly decays into daughter nuclei plus several neutrons, usually 3. So 3, 1, 0, N. The point being that this happens because this 236 uranium that's formed is unstable. So as a result, it will split into these daughter nuclei and these extra neutrons. So our answer then is that the neutron is absorbed by the uranium-235 nucleus. This causes the nucleus to split into daughter nuclei and several neutrons. The next part of the question says, a thermal nuclear reactor produces radioactive waste. State the source of this waste and discuss some of the problems faced in dealing with the waste at various stages of its treatment. Your answer should include the main source of the most dangerous waste, a brief outline of how the waste is treated, and the problems faced in dealing with the waste, with suggestions for overcoming these problems. Note that as a 6-mark question, this question will assess not only the subject knowledge provided, but also the layout of information. Therefore, it is important to organize the information in a logical way to gain all of the marks accessible. So in this process, what's going on is that the source of the main source of the most dangerous waste are the radioactive daughter nuclei that come from the fission of uranium-235. In order to treat the waste, first it is placed in ponds or another water source. This has two purposes. One, to remove the excess heat, since the waste will be very hot. Secondly, the water will absorb some of the radioactive emissions, and so by the time the waste is removed from the water, it will be less radioactive. After this, the plutonium and uranium are separated to be recycled. This leaves the waste that contains the daughter nuclei, which is vertified or made into solid glass. The reason for turning it into glass is because if it was in liquid form, it's easier for the waste to leak, and this can cause problems down the line. After this, the waste is placed in lead containers and stored deep underground. The reason for this is that lead is highly attenuating and so will help to absorb the radiation produced by the waste. Equally, storing it deep underground also assists in preventing the waste from contaminating the wider environment due to radioactive emissions. This is because the waste stored deep underground will be in geologically stable areas, and therefore it is unlikely to be disturbed. In order to get full marks in this question, you needed to provide 6 points, and at least the source of the waste needed to be provided, at least 2 steps of the treatment process, and finally at least 3 problems and how they are overcome in the treatment process needed to be mentioned. In questions such as these, the structure that I recommend taking is to follow the bullet points. In other words, firstly you should state the source of the waste, then you should give the brief outline, and finally you should talk about the problems. I have produced one sample answer, which is what you're seeing at the moment. This question is about nuclear physics. The question says, calculate the binding energy in megaelectron volts of a nucleus of 5927 cobalt. And they tell us that the nuclear mass of 5927 cobalt is 58.93320 U, where U is the atomic mass unit. In order to answer this question, it is helpful to consider the mass defect. This quantity describes the difference in the mass of all the nucleons before they come together and after they come together to form the cobalt nucleus. In this case, what we see is that the total mass of the nucleons before they all come together and the total mass after they form the cobalt nucleus is not the same. This is the idea of the mass defect. Now, because the total mass of all the nucleons before they form the nucleus is going to be higher than the total mass of the cobalt nucleus, then we see that we've lost some mass. Now, this mass has been converted into the binding energy and is released whenever the nucleus is formed. This can be seen by using the equation delta E is equal to delta M times by c squared, where delta M is our mass defect, and then we just multiply by the speed of light squared in order to get the energy that that's equivalent to. This is Einstein's equation. So what we see then is that the energy given out is the binding energy. This is directly related to the mass defect. So our strategy then is going to be to calculate the mass defect and then convert that to an energy, and that will represent the binding energy. So first, we need to calculate the mass of all the nucleons before they form the nucleus. The question has given us a hint, which is to give them the nuclear mass of cobalt in terms of the atomic mass unit. Therefore, to save us converting answers, we should calculate the mass of all the nucleons in terms of the atomic mass unit as well. So this is equal to the number of protons times by the mass of a proton in the atomic mass unit, 1.00728, plus, so this is the protons, plus 59 minus 27. So this comes from the mass number minus the atomic number. So the atomic number is the number of protons, which we used here. And so the difference between the two gives you the number of neutrons, since the mass number describes the total number of all nucleons in the nucleus. And then we multiply this by the mass of a neutron, which gives 1.00867. And so that is given by 59.474. Remember that this is in the atomic mass unit, so I'll write U afterwards. Now we calculate the mass defect, difference between the mass of all the nucleons before and the nucleus formed. So that's equal to 59.474 minus the nuclear mass of cobalt. So that's 93320, which gives us 0.5408 in U. From here, we need to convert this mass into an equivalent energy in megaelectron volts. Luckily, there is a conversion given on the datasheet for this. Specifically, we can use the fact that one atomic mass unit is equivalent to 931.5 mega electron volts. Therefore, we can say that if we have the mass defect delta M, then we can convert it to an energy delta E. Therefore, to get our answer, we need to multiply delta M in U times by 9.31.5 mega electron volts. So this is 931.5 mega electron volts per atomic mass unit. So this cancels out to get us 931.5 times delta M mega electron volts. This gives us that delta E is equal to 931.5 multiplied by 0.5408, which is equal to 503.7552 mega electron volts, which is equal to 503.8 mega electron volts to 4 significant figures. Now, the choice of 4 significant figures here is an interesting one. The reason for it is because we are limited by the precision of the lowest precision piece of data that we've been given. Now, most of the data in this question has actually been given to high precision, i.e. we've had the mass of the proton in the atomic mass unit is to 6 significant figures, the same with the neutron. However, this conversion here, 931.5 MeV, is to 4 significant figures. So this is the degree of precision to which we're limited to, because we can't say anything more about the conversion we've made than that it is accurate to 4 significant figures. Therefore, we give our answer to 4 significant figures. In this question, we got 1 mark for an attempt to calculate the mass defect, this subtraction here. We got a 2nd mark for calculating the mass defect correctly as 0.5408. And we got our 3rd mark for converting the mass defect into the binding energy by multiplying by 931.5, like so, and then getting our correct final answer. The next part of the question says, a nucleus of iron 59, decays into a stable nucleus of cobalt-59. It decays by beta minus emission, followed by the emission of gamma radiation, as the cobalt-59 nucleus de-excites into its ground state. The total energy released when the iron-59 nucleus decays is 2.52 times 10 to the minus 13 joules. The iron-59 nucleus can decay to one of 3 excited states, the cobalt-59 nucleus, as shown in figure 5. The energies of the excited states are shown relative to the ground state. So we can see in figure 5 that the 3 ground states have energies 2.29 times 10 to the minus 13 joules is the highest excited state, 2.06 times 10 to the minus 13 is the middle excited state, and 1.76 times 10 to the minus 13 joules is the lowest excited state. And then the ground state has an energy of 0 relative to the ground state, because it is the ground state. So the question wants us to calculate the maximum possible kinetic energy in mega electron volts of the beta minus particle emitted when the iron-59 nucleus decays into an excited state that has energy above the ground state. In order to do this question, we should consider an equation for how the decay happens. Specifically, we have that Fe59 goes to an excited state of cobalt, which is also cobalt-59, and then the star represents that it's excited, in addition to a beta minus particle and an electron antineutrino. The cobalt nucleus then decays into the ground state of cobalt plus at least 1 photon. So the reason that the question says maximum possible kinetic energy is because whenever the iron nucleus decays, we could have that some of the energy goes to the beta minus particle and some goes to the electron antineutrino. So for this part of the question then, we want to assume all energy goes to the beta minus, rather than being spread in some way between the electron antineutrino and the beta minus particle. So now we need to think about how the beta minus particle is going to get the maximum possible kinetic energy. So the energy that it gets is going to be equal to the difference between the two states. In other words, we'll go from the iron 59 nucleus to either to the highest excited state, to the middle excited state, or to the lowest excited state. This is the largest energy gap, the difference between the iron 59 nucleus and the lowest excited state. So this gives us the maximum energy of the beta minus. So this means that what we want to do is we want to calculate the energy gap between the Fe59 nucleus and the lowest excited state. So we know that the total energy released whenever the Fe29 decays to the ground state is 2.52 times 10 to the minus 13 joules. This is because we're told earlier in the question that the total energy released is this value. So therefore this corresponds to an arrow which would go from the iron 59 all the way to the cobalt at the bottom. So this means that the energy difference between the Fe59 and lowest excited state is delta E is equal to 2.52 times 10 to the minus 13, the total energy that could be released, minus how far above the ground state the lowest excited state is, i.e. 1.76 or 1.76 times 10 to the minus 13. These are in joules. So doing that calculation, we find that the energy difference delta E is 0.76 times 10 to the minus 13. So this is in joules. Then we have to convert to electron volts. So to do this, we take the energy in joules and we divide by the electron charge, because the definition of an electron volt is that 1 electron volt is equal to 1.60 times 10 to the minus 19 joules. It's the potential difference it's the energy that you get if you accelerate an electron through a potential difference of 1 volt. So what you get then, delta E divided by 1.60 times 10 to the minus 19 will tell me what my energy is in electron volts. So this is 2 electron volts, but we also want to convert this to mega electron volts rather than just electron volts. So we also need to divide by 10 to the 6 to turn it from electron volts into mega electron volts. Therefore, doing this calculation, we find that we get 0.76 times 10 to the minus 13 divided by 1.60 times 10 to the minus 19 times 10 to the 6, which gets us 0.475 MeV. And this is just equal to 0.448 MeV to two significant figures. In this question, we got 1 mark for calculating the correct energy difference, delta E, and we got another mark for converting that correctly into a kinetic energy of 0.48 megaelectronvolts. Note that in this question, even though the answer quoted in the mark scheme is given to 2 significant figures, all the data that has been given is to 3 significant figures. Therefore, you could leave your answer as 3 significant figures and still be confident about its precision. The next part of the question says, following the production of excited states of 5927 cobalt, gamma radiation of discrete wavelengths is emitted. State the maximum number of discrete wavelengths that could be emitted. In order to answer this question, we need to relate the difference between the energy levels of the nucleus and the photon energy and its wavelength. So specifically, what's going to happen is that if I arrive in one of the excited states and then I jump down a level, then I'm going to produce a photon, like so. So the difference between the levels gives the photon energy. Now, this photon energy is related to its frequency by the equation E is equal to hf. We also know that the frequency is related to the wave speed, which is the speed of light here, by the equation C is equal to f times lambda. We want to form an equation that relates lambda to E. Therefore, we can rearrange this equation C is f lambda to form f is C divided by lambda. Therefore, we have E is equal to h C divided by lambda, just by substituting the equation for F into the equation for E. Therefore, one specific energy difference gives one specific wavelength. So now we need to consider the different ways that we could decay from the iron 59 nucleus down to the ground state. So firstly, I could either do 3 to 2 to 1 to 0, like so, and each time I would produce a photon. So in other words, we go from level 3, the highest excited state, to level 2, to level 1, to level 0, like so. So 0 is the ground state here. Now, I could also go straight from 3 to 1, like so, and then I could decay to the ground state through the 1 to 0 one, as already mentioned. Another photon we could get then from level 2 to level 0, since this corresponds to a different energy difference again. Finally, we could also go from level 3 to level 0, so straight from the top. This constitutes 6 different paths through which we could decay from the top level to the bottom. If we decayed from the iron nucleus straight to level 2 or level 1, then we would still get the same kind of photons. For example, we would get 2 to 1 and then 1 to 0, or we could get 2 to 0, but we wouldn't get quite so many. But this doesn't include all possibilities. Therefore, by stating all the decays that can happen from the highest level, we've included all the possibilities for different photon energies that we could get as the nucleus de-excites to the cobalt-59 in the ground state. Therefore, there are 6 different photon energies, and because there are 6 different photon energies, there are 6 different photon wavelengths. Therefore, the answer to this question is 6. The last part of the question says, calculate the longest wavelength of the emitted gamma radiation. So to do this question, we can use the equation that we derived in the previous part, namely that the energy of the gamma photon is given by h times c, so h is Planck's constant, c is the speed of light, divided by lambda, the wavelength. So what this means is that the longest wavelength corresponds to the lowest energy. Since when the energy is small, it means that hc divided by lambda has to be small, which means that lambda has to be very big. Therefore, we should be looking for the smallest energy difference on our diagram above. Returning to the diagram, what we see is that the smallest energy difference is between level 3 and level 2. If we subtract the energies of 3 and 2, or 2 from 3, then we get the smallest number compared if we subtracted the energy of 1 from 2 or the energy of 0 from 1. Therefore, the energy difference we want is corresponding to a photon being released from de-exciting from level 3 to level 2. So then, the smallest energy difference is between levels 3 and 2. Therefore, E is equal to the energy at level 3 minus the energy at level 2. This is given by 2.29 times 10 to the minus 13 in joules minus 2.06 times 10 to the minus 13, also in joules, which is equal to 0.23 times 10 to the minus 13 joules. Then we need to use the equation E is equal to hc over lambda, which we derived earlier, and substitute and then rearrange such that we make lambda the subject. So we multiply both sides by lambda and divide both sides by E. Then we substitute in the numbers. Specifically, we know that the Planck's constant h is given by 6.63 times 10 to the minus 34. C is given by 3 times 10 to the 8, and we worked out E earlier as 0.23 times 10 to the minus 13 joules. Therefore, doing that calculation, we find that lambda is given by 8.649593 ... times 10 to the minus 12 meters. And this is equal to 8.65 times 10 to the minus 12 to 3 significant figures. The choice of 3 significant figures here is because all the data in the question and all our conversions are given to 3 significant figures. Therefore, we can leave our answer to 3 significant figures and still be confident in its precision. Therefore, this is our answer. In this question, we got 1 mark for calculating the energy difference correctly. We got 1 mark for an attempted use of lambda is hc over E and substituting in, and we got 1 mark for our correct final answer. This question is about gravitational fields. The question says, state what is represented by gravitational field lines. Gravitational field lines represent the direction and relative size of a force that acts on a massive object inside a gravitational field. So for example, if I place a massive object where there's a field line going directly downwards, then we expect to get a force following the direction of the field line, so the force will also go directly downwards. Also remember that the density of the lines represents the strength of the force. More field lines implies more force. inside an area of given size. So our answer to this question is that the gravitational field lines represent the direction of the force and relative size of that force that act upon a massive object inside a gravitational field. In this question, the three key concepts to talk about were the direction of the force, the fact that it was a force, and to say that it acts upon a mass. The next part of the question says, Figure 6 shows the gravitational field above a small horizontal region on the surface of the Earth. So here we have field lines that are straight and parallel and uniform going into J, and then towards K they bend a bit until at K they're back to going directly in, and then on the right hand side they're bending in the same way as before. So the question says, suggest why the field lines converge over a small area at K. So, like we said in the previous part of the question, denser field lines represent a stronger field. So what this means is that the field is getting stronger as you get closer to K, until it's quite strong right around K. So what this means is that because the source of the gravitational field is mass, we must have more mass relatively close to K, or around K, because this is generating an increased gravitational field compared to the gravitational field at J. What this means then is that because we can measure density as mass divided by volume, we can say that the ground, in a patch of ground at K, this patch is denser than over here. So patches of mass around K are going to be denser than mass elsewhere on the surface of the Earth. Therefore, what we'll need to say is that since field lines at K are closer together, the field is stronger. Therefore, the material at K has a higher density than at J. In this question, we got 1 mark for saying that the field is stronger, which is due to the field lines being closer together, but the mark was for saying the field is stronger. And we got 1 mark for saying that the material at K has a higher density. You didn't need to quantify it by saying than the surrounding material, but it's nice to have. The next part of the question says, a ball traveling at constant speed passes position J, moving towards position K in figure 6. Assume friction is negligible, and it wants us to explain any change in speed of the ball as it approaches K. So we don't need to worry about it leaving K, just approaching K. In order to do this question, it's helpful to consider the forces acting upon the ball as it rolls. We've been told that friction is negligible, so whenever there's no sideways force acting on the ball, it will just keep going at a constant speed. This is because the gravitational force downwards, say around J, so this is where we're near J, So the weight is equal to the normal reaction force. Okay, so that's what's happening when we're near J. When we're near K, though, what's happening is our gravitational force now has a component going to the right. This is because the field lines point down and to the right, so there is a component going to the right. So what we see then is that the forces acting on the ball are modified to something like this. We have some component of the gravitational force which is going downwards. So in this case, I'll label the gravitational force F subscript G. So Fg, and there's one component going downwards, and then there's also a component going to the right. So Fg to the right. This is because this force, which is pointing in something like this direction, can be resolved into two components, the one going to the right, going down, like so. We then also have the normal reaction force, which, since the ball isn't going downwards because the surface is horizontal, the normal reaction force must still balance the downwards component of gravity. So in this case, N is equal to Fg down. So what this means then is that at K, the ball experiences a resultant force to the right. Because it experiences a resultant force to the right, it therefore must accelerate. This is because of Newton's second law, which says that the force acting on an object is proportional to its acceleration, with the constant of proportionality being the mass. Or in other words, F equals ma. Therefore, if we have a resultant force acting upon an object, then we get an acceleration. Therefore, the speed increases. So our answer is that the ball accelerates and speeds up, or increases in speed, since there is a component of the gravitational force acting to the right. So this means that because of this gravitational force acting to the right, we can use the fact that a force is proportional to an acceleration from Newton's second law, is ma. So if we have a force pulling the ball to the right, we must therefore also have our acceleration. In this question, we got 1 mark for stating the effect on the motion of the ball, in other words, that it accelerates, and we get our 2nd mark for explaining why, because there's a component of the gravitational force acting to the right. The next part of the question is about electric fields, and it says, Figure 7 shows lines of force for the electric field surrounding two charged objects, L and M. And so we see one charge L and another charge M. And they're of opposite charges because the field lines from one charge go into the other. The question says, explain why the lines of force shown in figure 7 cannot represent a gravitational field. In order to do this question, we need to remember that gravity is an attractive force, and an attractive force only. So what this means then is that if I have two gravitational objects interacting, then I can never have the field lines from one object coming out like this. So field lines cannot come out, because this represents the direction of the force that would act on the other object. What this means is that if I am this second object here, then I'm going to get repelled. And masses never repel, they only attract. Therefore, in this case, what we see is that there are field lines coming out of L, which means that L would repel a positive charge. So what that means is that if we were talking about masses, this would cause a mass to be repelled too. So this can't happen. So our answer then is that the lines of gravitational force, or the gravitational field lines, must always point into a massive object. The next part of the question says, state which object, L or M, has a charge with the greater magnitude. So remember, the objects with charges of greater magnitude generate larger forces around them. So larger magnitude charge implies a force of larger magnitude. Now, since the force, the relative magnitude of the force, is represented by the density of the field lines, what that means is that because the field lines are more dense around L, it's generating forces of larger magnitude. Therefore, L must have a charge of greater magnitude. So the answer is L for that part. As for which object has the positive charge, we know that for positive objects, they want to repel positive charges, and electric field lines represent direction a small positive chest charge will move. So what that means is that positive charges have lines coming out because they want to repel other positive charges. Whereas negative objects, they want to attract positive charges, so their field lines must be going in towards them. So they want to attract positive charges. Then, because we know that the field lines are leaving L, it must have a positive charge. Therefore, the answer for this one is also L. The last part of the question says, draw on figure 7 an equipotential line that passes through point N. Do not extend your line beyond the given field lines. So in order to answer this question, we need to remember what an equipotential line represents. So an equipotential represents a part of space where the potential is constant. What this means in relation to the fields is that fields can be considered as gradients of a potential. So the direction of the field lines tell you what direction the potential is changing in. So what this means then is that if I want to consider regions where the potential doesn't change, then it shouldn't change along right angles to the potential, to the field lines. Because if the field lines represent the direction that the potential is changing in, if I go perpendicular to that direction, the potential must not be changing. Therefore, what I'm looking to do is I'm looking to draw a line from N that is at right angles to all the field lines. I'll start at N and I'll start by going upwards. So I want this line to remain at right angles at all times, whilst taking the shortest path between the different field lines. This is because if we were to take paths that were longer than the shortest path, then over this path the potential would actually change. Because what you can imagine is that between L and M, there are additional lines of force that tell you how a positive charge would move. So actually you also want to be perpendicular to all of them too. Therefore, you're looking to take the shortest possible path between the field lines. So our field line, or our equipotential line rather, should look something like this. We need to go down as well, so we're looking at something like this. And the aim is that we're trying to make this as symmetric as possible in the top and bottom half. So like so. And this line would be worth 2 marks. The criteria for this line to be worth 2 marks then was that the line had to be at right angles to the field lines. We also need to have that the line is symmetrical about a line of symmetry, which I'm going to draw now and label 1. So it's the line of symmetry that goes directly through halfway between each charge and through N. So because the field is symmetric about this point, so too must the equipotential line. Finally, the line had to bend to the left. Which is what we were expecting when we drew the equipotential line in order to satisfy the criteria that I set out earlier. So these were the 3 criteria. These 2 were worth 1 mark, and this one was worth 1 mark. This question is about orbits. The question says, derive an expression to show that for satellites in a circular orbit, t squared is proportional to r cubed, where t is the period of orbit and r is the radius of the orbit. In order to do this question, we need to collect together a few facts about what we know about the orbit, specifically that satellites orbit under the gravitational force, and we are also told that the orbits are circular. So what this means is that we can use various equations relating to these 2 concepts, specifically that the gravitational force is given by F is equal to G, Newton's gravitational constant, multiplied by the mass of the object that the force is acting on, multiplied by the mass of the object that's generating the field, divided by the distance between them squared. This is like having a small mass and a big mass. So our small mass m will be the mass of the satellite. This will be the mass of the planet that it's orbiting about, like so, and then the distance between them is r. And then because we're dealing with circular orbits, we can use the fact that we have centripetal force which is given by F is equal to mv squared divided by r. So we need larger force to keep objects in tighter circles, because if r is very small, then F must become very big. And if we want to make objects go around a circle faster, then we must increase their speed as well. So v is the speed here, and m is the mass of the object. We also have that the velocity or the speed of an object is given by the distance traveled, 2 pi r radius of orbit divided by the time period. So this is just the circumference of a circle. And it takes t, big T, to orbit once. The reason I've collected these equations together is because we want to relate little r to big T, and we need to use other equations that contain little r in them. So our strategy is going to be first to eliminate F, because we need an equation that relates V to R. Then we have a second equation which relates V to R. And then we'll combine the two. And since one of them includes T, we'll get our final result. So doing that then, we can say that G, little m times big M divided by r squared, the gravitational force, that acts on the satellite, is equal to the centripetal force acting on it, because this force is making the satellite travel around in a circle, like so. So in this case, we can tidy it up, the m's cancel, and we're left with v squared is equal to gm divided by r, like so. So all I've done is I've multiplied both sides by r, and I've divided both sides by little m. Then we can use the fact that we're doing circular motion. So we can say that v is equal to 2 pi r divided by t. And so we can combine these two together. And what we get then is that by substituting in v, we have 2 pi r divided by t all squared is equal to gm divided by r. So tidying up then, if we multiply both sides by r and both sides by t squared, then we get t squared times gm is equal to 4 pi squared times by r cubed. So finally, we get t squared is equal to 4 pi squared divided by gm. Well, and that's all multiplied by r cubed. And since 4 pi squared over gm, and this is big M, remember, is a constant, we have that t squared is proportional to r cubed, which is what we were after. So in this question, we got 1 mark for identifying that we're dealing with gravitational forces and we're dealing with circular motion. So the centripetal force equation and the gravitational force equation. And we get 1 mark for combining them along with our other equation for V. So over here is our second mark, and then getting the result. The next part of the question says, Pluto is a dwarf planet. The mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers, compared to a mean orbital radius of 1.50 times 10 to the 8 kilometers for the Earth. Calculate in years the orbital period of Pluto. So in this question, we should use what we derived in the previous part, i.e. that the time period squared of a planet is proportional to the mean orbital radius cubed. Now, the reason that we want to use this is because at the moment, if we were to just consider Pluto on its own, then we would have to use the equation t squared is equal to 4 pi squared divided by gm divided by gm multiplied by r cubed. So this is a problem because we don't know the mass of the sun. So remember that big M represents the mass of the object that the satellite is orbiting. So in this case, we have the sun, we have both Earth and then Pluto orbiting. So that's going to be a problem. However, we know that t squared is proportional to r cubed. So that if I know data about two different planets, then I can use what I know from the orbit of one planet to predict what will happen to the orbit of the second one. To see this then, we can consider this equation for the Earth versus this equation for Pluto. So Earth has subscripts e, so te squared is equal to 4 pi squared divided by gm, and this stuff is all the same, times by re cubed. So re is the orbital radius of the Earth around the Sun. We also know that Tp for Pluto is squared is given by the same equation, but with a subscript p on the r. So now we can do Tp squared divided by Te squared, and that gives us 4 pi squared over gm divided by 4 pi squared over gm times by rp cubed divided by re cubed. And so these cancel, leaving us with Tp over Te all squared, where I've taken the two inside a bracket, and that's equal to Rp over Re cubed. So, because we know about the orbit of the Earth, we can eliminate the need to know about the mass of the Sun. And instead we can just use the relation that we've derived. The other thing we need to know is that at the moment we still have one bit of information unknown, which is that we haven't been told in the question rather what the orbital period of the Earth is. But luckily, we know that the orbital period of the Earth is just 1 year, because we define a year as the time taken for the Earth to orbit the Sun once. Therefore, what we can say is that Tp all squared is equal to Rp divided by Re all squared, or to the power of 3 rather, multiplied by 1 year all squared. So then we can square root this equation to find that Rp divided by Re to the 3 over 2 times 1 year is our answer. So now we can substitute in the numbers for this. And so we put in the orbital radius of Pluto, 5.91 times 10 to the 9 kilometers. And then we have 1.50 times 10 to the 8 kilometers. And the reason I've written it like this is because we can see from this that the kilometers and most of the powers of 10 actually cancel with each other. So the kilometers cancel and this cancels, leaving us just with 10. So in order to save yourself time, you don't need to enter the times 10 to the 3 that converts kilometers to meters or anything like that whenever you're dividing two quantities that are in the same units by each other, because those units will always cancel. Therefore, we could have just written 5.91 times 10 to the 9 divided by 1.50 times 10 to the 8. This can just save us a bit of time here and there. So what this will give us then is an answer of 247.3 ... years if you do that calculation. And so, since the data in the question is given to 3 significant figures, then we can say that our orbital period of Pluto is 247 years. So, in this question, we got 1 mark for substituting data into an equation that's an attempt to use t squared is proportional to r cubed. And we got 1 mark for our correct final answer. The next part of the question says, a small mass released from rest just above the surface of Pluto has an acceleration of 0.617 meters per second squared. We're told to assume Pluto has no atmosphere that could provide any resistance to motion, which signifies no air resistance. And they want us to calculate the mass of Pluto and to give our answer to an appropriate number of significant figures. So usually in a question like this, we'll get 1 mark for our answer being to a correct number of significant figures, regardless of what our answer actually is. And they tell us, which is a hint, that the radius of Pluto is 1.19 times 10 to the 6 meters. In order to do this question, we're looking for an equation which has the distance of an object between the object and the center of Pluto. So we're looking for an equation that has r. We're looking for an equation that has the mass of Pluto, which would be big M in this situation. And we're looking for an equation which has an acceleration in it, a. So the natural choice for gravitational problems that has both the mass and the distance between 2 objects in it is the gravitational force or the potential. So force or potential. But because we're told acceleration as well, we know that we probably want to be using Newton's second law. So we want to be using gravitational force here. So to go further then, we can say that the gravitational force F is equal to G times big M times by little m. So this is the mass, the small mass, divided by the distance between the center of the small mass and the center of the big mass, which is Pluto. So this is what we mean. Except in this case, the object is just above the surface of Pluto. So we can amend our diagram slightly. This is little m, this is big M, like so. And then we also know that F is equal to ma from Newton's second law. Therefore, we can set these equal to each other. So we have m times a is equal to g times m times little m divided by r squared. So the resultant force acting on the mass is just equal to the gravitational force. We're told that there's no air resistance or other forces acting on the mass that might complicate things. So then we cancel m from both sides, and we're left with the equation a is equal to g m divided by r squared. Now we're interested in the mass of Pluto, so we should rearrange this to get m is equal to a times r squared divided by g. If we substitute numbers in for this, we get 0.617 times by the radius of Pluto. So we've assumed that we're right on the surface of Pluto. So we just take the object as being as a distance of the radius away from the center of Pluto, divided by Newton's gravitational constant g, which is 6.67 times 10 to the minus 11. And if you do that, then you get m is equal to 1.30994 5 dot 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 times 10 to the 22. Now we need to consider the number of significant figures that we give our answer to. And so the name of the game when we do a question like this is always to give the answer to the same degree of precision as the data given in the question. So in this case, this is to 3 significant figures. The radius of Pluto is given to 3 significant figures. We can get the value of g off the datasheet. In fact, I'll write that elsewhere. So therefore, all the data that we have is to 3 significant figures. So whenever we choose the degree of precision that we write our answer down to, it's always to the lowest degree of precision that we have a piece of data to. In this case, since they're all to 3 significant figures, we're okay to write our answer to 3 significant figures. So our answer would be 1.31 times 10 to the 22 kilograms. We can put 3 significant figures down, like so. So in this question, we got 1 mark for an application of m is ar squared divided by g, to get that. And trying to substitute in, we got 1 mark for a correct final answer, and we get 1 mark for rounding it to 3 significant figures. If we had done an incorrect calculation, but still put our answer here to 3 significant figures, and as long as we had provided some working, then we would still be able to get the 3 significant figures mark without necessarily getting the answer mark. The last part of the question says, Figure 8 shows the variation in gravitational potential with distance from the center of Pluto for points at and above its surface. So we see that the gravitational potential starts very negative and is increasing, and increases more slowly as you get further and further away from the center of Pluto. The question then says, a meteorite hits Pluto and ejects a lump of ice from the surface that travels vertically at its initial speed of 1,400 meters per second. Determine whether this lump of ice can escape from Pluto. So in order to answer this question, it's convenient to consider the energy transfers that are going to have to occur for the lump to start on the surface of Pluto and then move upwards. In other words, we start with our lump and it's moving away with a certain amount of energy. Distribution to the energy of the meteorite will be in 2 forms. It will have kinetic energy and it will have potential energy. So the kinetic energy we can see comes from the formula Ek is equal to 1/2 times by the mass of the meteorite times by its velocity squared. And the potential energy comes from the gravitational potential. So it's from the graph above. Specifically, the gravitational potential energy is equal to the gravitational potential multiplied by the mass of the object, m. So in order for my object to escape from Pluto completely, what's going to happen is I'm going to have to use up some of my kinetic energy and convert that into gravitational potential energy. So if we consider the lump escaping from Pluto, or escaped from Pluto, what has to happen is I have to start with a certain amount of Ek and a potential energy that's less than 0. And then as I move further away from Pluto on this graph, what I'm going to find is that I get closer and closer to not having any gravitational potential energy. And then when I've finally escaped from Pluto, I have no gravitational potential energy. I'm at 0. So the point is that some of my kinetic energy is converted to gravitational potential energy, such that when I've escaped from Pluto, I've gone from a negative value of gravitational potential energy and increased it to become 0. This signifies having escaped. So therefore, I must have at least enough kinetic energy to cancel out to convert into gravitational potential energy so that I can escape. Note that if there's less kinetic energy than the value then actually I can't escape from Pluto, because at some point I won't have any more energy to convert into potential energy, and therefore I won't be able to escape, because I won't be able to get all the way out, and then Pluto will start pulling me back towards its surface. So the point then is that I want to calculate the kinetic energy and the potential energy and see which one of them has a larger magnitude. So in other words, I can calculate the kinetic energy, Ek, is equal to 1/2 times by the mass of the object, which we don't know, multiplied by its velocity, which is 1,400 squared. And doing that calculation, what we find is that we have 9.8 times 10 to the 5 times by m. As for the potential energy, we need to know how negative that is when the lump starts on the surface of Pluto. So we want to read off this value here. Reading that off, that's approximately minus 7.4 times 10 to the 5. And that's joules per kilogram, because we're dealing with the potential, which is what's in the graph, not the potential energy. So then, we know that the potential energy, EP, is equal to minus 7.4 times 10 to the 5 multiplied by the mass of the lump, which is m, and we still don't know this. And so, like we said, we want to have enough kinetic energy that we can cancel out all the potential energy and be left with no potential energy. So in other words, we need to convert some of this to potential so that we go from minus 7.4 to 0. To go from minus 7.4 to 0, we need at least 7.4 times 10 to the 5 times m of kinetic energy. So in other words, the criteria we're looking for is that 9.8 times 10 to the 5 times m is greater than 7.4 times 10 to the 5 times m. So this represents the fact that we have enough kinetic energy to convert to potential energy such that we can lift the lump out of the gravitational potential of Pluto, and thus the lump can escape. So hang on, let me just write that in a slightly nicer way. Like so. Okay, and because this kinetic energy is indeed greater in magnitude than the magnitude of the potential energy, I have enough that I can convert to potential energy for the lump to escape. Thus, our answer is that yes, the lump can escape Pluto. As it has enough kinetic energy to escape. Note that we didn't actually ever need to know the mass of the lump because we were dealing with the gravitational potential, which is related to the gravitational potential energy by multiplying by the mass, and we had the kinetic energy, which contains a factor of the mass. So because it appears on both sides, we didn't ever actually need to know what m was in order to do this calculation. In this question, we got 1 mark for calculating the kinetic energy, 1 mark for calculating the energy needed to escape, which is the negative of the gravitational potential energy, and then we got 1 mark for comparing the two and seeing that the lump can escape because it has enough kinetic energy. This question is about specific heat capacity. The question says, a continuous stream of water falls for a vertical distance of 100 meters. Assume that no thermal energy is transferred to the surroundings, and the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. What is the temperature difference of the water between the top and the bottom of the waterfall? In order to answer this question, it is helpful to consider the energy transfers that are involved with the water falling through the vertical distance. Specifically, if I have a particle of water that starts at the top of the 100 meters and falls the whole way to the bottom of the 100 meters, then there is a transfer of gravitational potential energy. Since the water is flowing in a waterfall, when it hits the bottom, it has to hit the ground and then flow off. What this means then is that all the gravitational potential energy, which it has at the top, will be converted to kinetic energy, and then from kinetic energy it will be converted to thermal energy. This is because if my kinetic energy corresponds to the water particle falling down, then the velocity is in the downwards direction, and this velocity has to be removed whenever the water hits the ground. Therefore, the kinetic energy that comes from that downwards velocity will be turned into thermal energy. So by conservation of energy, and from the assumption that no thermal energy is transferred to the surroundings, we know that the gravitational potential energy is that the water had at the top of the waterfall has to be equal to the thermal energy at the bottom of the waterfall. Or specifically, the thermal energy added to the water particle. So what this means then is that we can express the formula for the gravitational potential energy, EP is equal to mgh, as equal to the formula given for the energy difference whenever you heat something up for a temperature difference delta theta, specifically that you have mc delta theta. So this is the energy gain of a substance if heated through delta theta. So just to define the symbols in these equations, m is the mass of the object that's falling, or the mass of the object that's being heated. G is the acceleration due to gravity, and h is the height through which the water particles fall, which in this case is 100 meters. C is the specific heat capacity, in this case of water, and this tells us how much energy we need to heat 1 kilogram of the water by 1 Kelvin, and delta theta is the temperature change. So therefore, we can say that through conservation of energy, these two are equal, and we can rearrange for the temperature change. Specifically, delta theta is equal to mgh divided by mc. And here we can see that the m's cancel with each other. Therefore, we're left with delta theta is equal to gh divided by c. So what this says then is that the temperature change is increased by having a larger acceleration due to gravity. That would correspond to us having more gravitational potential energy at the start, or to falling for a larger height, and decreases if we need more energy to heat a kilogram of water by 1 degree, or by 1 Kelvin. So then we can substitute in the numbers we know for these quantities, specifically that G is 9.81, H is 100, and C is equal to 4,200. And when we do that, we get 0.23357 ... which is approximately 0.23 Kelvin. So our answer is B. This question is about specific heat capacity and power. The question says, a student measures the power of a microwave oven. He places 200 grams of water at 23 degrees Celsius into the microwave and heats it on full power for 1 minute. When he removes it, the temperature of the water is 79 degrees Celsius. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. What is the average rate at which thermal energy is gained by the water? In this question, because we have been told that we're considering power, it's helpful to consider the equation for the power produced by an object, which is the rate at which it transfers energy divided by the time taken in which it transfers that energy. Because we're told that an object is heated and there's a temperature change, it's also helpful to consider the change in energy E due to heating an object, which is given by the mass of that object multiplied by its specific heat capacity multiplied by the change in temperature, delta theta. So what we see here is that we've been given an initial temperature, theta I, final temperature, theta F, because we end at 79 degrees Celsius and we start at 23 degrees Celsius. We've been given a mass of water. We've been given how long the water is heated for, the time. And we've also been given the specific heat capacity. Our aim is to calculate the average rate at which thermal energy is gained by the water, which is just equal to the power dissipated in the water, P. So therefore, we can first calculate the energy transferred to the water. So we do that by using E is equal to the mass, which is 200 times 10 to the minus 3, because we've been given it in grams and not kilograms. So this is grams to kilograms. So the kilo prefix just brings in a factor of 10 to the minus 3. Then we include the specific heat capacity, 4,200. And then we have the temperature change, which is the final temperature minus the initial temperature. And note that even though our temperatures have been given in Celsius, we don't need to convert them to Kelvin here, because if we've converted them both to Kelvin, the temperature difference would still be the same. This is because if I had 79 plus 273, and then I subtracted 23 plus 273, the extra 273s, which come from converting to Kelvin, so to convert any Celsius temperature to Kelvin, you add 273. These two just cancel out. Therefore, we don't need to waste time converting this in the exam. Then, if you take this number that we get for the energy, you can substitute it into the equation for the power, which is given by, again, 200 times 10 to the minus 3 times by 4,200 times by the temperature difference, which is 79 minus 23, which is 56. Then we divide by the time taken to transfer that amount of energy to the water. So this was 1 minute, so we need to do 1 minute times by 60. So this is minutes into seconds. If you do this calculation, then you find that the power dissipated in the water is approximately 784 watts, which gives us A. Therefore, our answer is A, to two significant figures. This question is about converting the mass of a total substance into the number of molecules that are contained within that substance. The question says, the composition of a carbon dioxide molecule is 1 atom of 12 carbon and 2 atoms of 16 oxygen. What is the number of molecules of CO2 in 2.2 kilograms of the gas? In order to answer this question, we're going to use the fact that the number of molecules is given by the total mass of the substance divided by the mass of one molecule. This is because if we know what one molecule weighs, then we know that if we have the total mass, then it must be made up of a certain number of those individual molecules. Therefore, if I multiply the number of molecules by the mass of one molecule, I should get the total mass. To get the mass of one molecule, mass of one CO2, then we need to use the fact that we've been given mass numbers. Specifically, we've got 12 carbon and 16 oxygen. So the 12 in 12 carbon corresponds to the mass of the atom in units of the atomic mass unit. So we have 12U from the carbon plus 2, because we have 2 oxygens. So this is from oxygen multiplied by 16 times by U. So this will give us the total mass of one carbon dioxide molecule in terms of the atomic mass unit. Therefore, our total number of molecules, N, is given by the mass divided by this, which is 12 plus 2 times 16U, which is 44 times by U. So substituting in, we have that M is equal to 2.2 kilograms, and we have that the mass of one carbon dioxide molecule is equal to 44 times by 1.661 times 10 to the minus 27. And that's in kilograms. And we've just taken this value from the datasheet. So doing that calculation, we find that N is equal to 3.010 ... times 10 to the 25, which is approximately equal to 3.0 times 10 to the 25, which means that our answer has to be C. This question is about internal energy. The question says, what is the total internal energy of 2.4 moles of an ideal gas which has a temperature of 15 degrees Celsius? In order to do this question, we first need to understand the definition of total internal energy, which is the sum of the randomly distributed kinetic and potential energies of the gas molecules. Therefore, in order to work out the total internal energy of the entire gas, we need to work out the average energy of one gas particle and multiply it by the number of gas particles, and this will correspond to the total internal energy on average, which is how the total internal energy is defined. So then, in order to make progress, we need to figure out what the kinetic and potential energies involved are. Now, we've been told that we're dealing with an ideal gas, and one of the assumptions in an ideal gas is that the interactions between gas particles are negligible except during collisions. What this means then is that there's no potential energy that comes from any of the interactions between the particles, because most of the time there are no interactions between the particles. Therefore, the only energy is kinetic of any given particle. So that's the only part of the kinetic and potential energies that contribute to the internal energy. So therefore, we can say that the energy of one particle is given by the equation on the datasheet, 3/2 times kb times by t. Now we can use that the total number of particles in the gas, n, is equal to the number of moles of the gas multiplied by the number of particles in 1 mole, as the number of moles is just a way of counting the number of particles present in the gas. Therefore, we can say that the total energy, or the internal energy, is given by n, little n, which comes from up here, times by Na, Avogadro's number, 6.022 times 10 to the 23, times by 3/2 times kb, Boltzmann's constant, times by t. So substituting in numbers, what we find is that we have 2.4 times 6.022 times 10 to the 23 times 3 over 2 times 1.38 times 10 to the 23 minus 23 times by the temperature. Now, in putting the temperature in this equation, we have to make sure to convert to Kelvin. This is because we're dealing with a single temperature rather than temperature difference, so the units in which we calculate a temperature are important. Therefore, the temperature is equal to 15 from the Celsius plus 273. This is to convert into Kelvin. So then, if we put that into our calculation for T, then what we find is that the total energy is given by 8616.18 ... which is approximately 8.6 times 10 to the 3 joules. Therefore, our answer is D. This question is about gravitational fields. The question says, Charon is a moon of Pluto that has a mass equal to 1/9 that of Pluto. The distance between the center of Pluto and the center of Charon is D. X is the point at which the resultant gravitational field due to Pluto and Charon is 0. What is the distance of X from the center of Pluto? In order to do this question, we need to consider the definition of the gravitational field strength. Specifically, that for a source mass m, the gravitational field strength at a distance r from the center of that object, as long as you're outside the object, we have that it's g times m divided by r squared. So m, the mass of the body, r, the distance from the center of that body, provided you're outside it, and g is Newton's gravitational constant. And so what's happening in this problem is that we have a gravitational field from Pluto and a gravitational field from Charon. And because these are both massive objects, they're going to want to pull in different directions. So at some point along the distance between them, there's going to be a point where they're both pulling with equal strength, so that a mass placed at that point won't feel a force upon it, because there's no resultant gravitational field. And that's what we're aiming to calculate, that point. So in order to do that, we're going to write an equation which relates these two gravitational field strengths at the point x. And specifically, we're going to start by defining the distance r from the center of Pluto. So somewhere along here, we have r, and r can be anywhere along this line between Pluto and Charon. And we're going to solve for where it is because it will be the position of x. So ultimately, we're going to find that rather than being there, it's going to correspond to the position at x. Then the distance from the center of Charon is going to be given by d minus r, because this total length here is d, as they marked on already. So we're going to write down an equation where we add the two gravitational fields together. And we have to be careful here, because this is going to be a vector sum, and if we do it wrong, then it won't reflect the directions of the gravitational fields. Specifically, because they're going in opposite directions, we can write g Pluto, which I'll abbreviate to GP in future, minus g Charon, which I'll abbreviate to GC in future, is equal to 0. So specifically then, substituting in our expression for GP and GC in terms of Pluto's mass and the distance from the center of each of those bodies, we have that this is equal to g times by the mass of Pluto, mp, so this is from GP, divided by r squared, because r is just the distance from the center of Pluto, minus g times by the mass of Charon, which I'll call mc, and which I'll soon write in terms of the mass of Pluto, divided by the distance from the center of Charon, which is d minus r. And then you square it, as per the definition. Next, we use what we're told in the question, that Charon has a mass of 1/9 that of Pluto, so MC is equal to 1/9 times by MP. So what that means then is that we can rewrite our equation up here like the following. So factorizing out G and MP, we're left with 1 over r squared minus 1 over 9 times by 1 over d minus r all squared, and that's equal to 0. So because we've got 0 on the left-hand side, we can just cancel out G and MP, divide both sides by G and MP, so they go away, and we're left with an equation including only R and D. So rearranging this equation a bit, if we move the 1 over 9, 1 over D minus R all squared to the other side, and then multiply both sides by R squared and both sides by 9 times by D minus R all squared, then we're left with R squared is equal to 9 D minus R squared. From there, we can take a square root. So we have R is equal to plus minus the square root of 9 is free, and the square root of D minus R squared is D minus R. Now remember to include the plus minus here. Because we have square rooted here, there is both a positive and a negative solution available that will give the same thing. You must include both of these and check which are reasonable for the problem that we're dealing with. So checking both cases, we have that either we take the plus case and we have R is equal to 3D minus 3R, which gives us 4R is equal to 3D, where R is equal to 3D over 4. So that one checks out, and that will actually end up being our answer. Just to show that the other case is not acceptable, we can then have R is equal to minus 3D plus 3R. Subtracting 3R from both sides, we obtain minus 2R is equal to minus 3D. And then dividing both sides by minus 2, we find R is equal to 3D divided by 2. This is no good because R is greater than D here, so this would correspond to us being further away than Charon. Therefore, this solution is invalid. Therefore, our only answer is R is 3D divided by 4, and so our answer has to be C. This question is about gravitational fields. The question says, the distance between the Sun and Mars varies from 2.1 times 10 to the 11 meters to 2.5 to 10 times 10 to the 11 meters. When Mars is closest to the Sun, the force of the gravitational attraction between them is F. What is the force of gravitational attraction between them when they are furthest apart? In order to answer this question, since we have been asked to consider the force of gravitational attraction between the two bodies, it is important to consider the equation for that force. Specifically, the force is equal to G times M divided by R squared. In this equation, we have the M is the mass of the Sun, and little m is the mass of Mars. And R is the distance between their centers. And those are what we're given in the question. In this problem, we haven't been given the masses of the Sun or Mars. Instead, we have the force and distance at two different points. Therefore, it is helpful to consider the idea of proportionality, specifically that the force given is proportional to 1 over the distance between the objects squared. So in this case, we can write two equations, one for the force whenever Mars is nearest to the Sun, and one for the force when Mars is furthest away. So those will have subscripts of n, and the far ones will have subscripts of f. So we have Fn is equal to G times m times big M times little m divided by Rn squared. And then for the far away ones, we have the same thing, but with f subscripts instead. So what we can see then is if we do f far divided by f near, then we have g m big M times little m divided by rf all squared divided by g big M times little m divided by Rn all squared. And what we see is that the g times big M times little m cancel each other out. So we're left with just an equation that looks like Rn squared divided by Rf squared, which, just to simplify slightly, is Rn divided by Rf all squared. So now we can translate this into the quantities given in the question, specifically that we know that Rn is equal to 2.1 times 10 to the 11, and Rf is 2.5 times 10 to the 11. And note that because they're in the same units and they divide each other, we don't need to include the times 10 to the 11 in our calculation. It's sufficient to do it like this, and therefore that helps us not make mistakes whenever we put it in the calculator, as well as saves us time. So therefore, we have that f far is equal to 2.1 divided by 2.5 all squared multiplied by fn, which is just f. Evaluating this, we get that the force at the furthest point is given by 0.7056 times by f, which is approximately equal to 0.71 times by f. Therefore, our answer is A. This question is about orbits and kinetic energy. The question says, a satellite X of mass m is in a concentric circular orbit of radius r about a planet of mass m. What is the kinetic energy of X? In order to answer this question, it is helpful to consolidate what we know about the planet and the satellite and what we're trying to find. Specifically, the satellite is orbiting in a circular orbit, which means that things like centripetal force and circular motion equations apply. We also have that it must be orbiting under the gravitational force, since this is between a planet and a satellite, and also because all the answers are in terms of Newton's gravitational constant g. And then finally, we also know that we're looking for the energy, so kinetic energy. So what each of these imply is that we can use various equations. For example, the kinetic energy is given by Ek is equal to 1/2 times m, the mass of the satellite, times by the velocity of the satellite all squared. The gravitational force is given by gmm over r all squared. And from a circular orbit, there are a number of different equations we can use, but since we know that we're dealing with gravitational force, it makes sense to consider that we have to be using centripetal force as well, so that we're doing mv squared divided by r. So now we need to figure out how we can get the kinetic energy. And specifically, we know that we have an equation for Ek contains v, the velocity, but v is not given in the question. So therefore we have to use our other equations to get v. So to do that, we use the circular orbit, the fact that we're in a circular orbit, which gives us the centripetal force equation, and that must be equal to the gravitational force. Therefore, doing that, we can write that the centripetal force must be equal to the gravitational force. The gravitational force is what provides the centripetal force in this case, which allows the satellite to continue moving in a circle. So at this point, we want to isolate v squared so we can put it back into the formula for the kinetic energy. And so what we get is that we have v squared is equal to g times big M divided by r. So what I've done here is divided both sides by little m, and then multiply both sides by r to get the equation v squared is gm divided by r. From there, we can then substitute that into the kinetic energy formula, which gives us a half times m times by v squared, which is equal to a half times m times by g big M divided by r, which, written in a slightly more aesthetically pleasing form, is g big M little m divided by 2r. Therefore, our answer is A. This question is about electric fields. The question says, two parallel metal plates of separation A carry equal and opposite charges. And here we see this represented in a diagram. Which graph best represents how the electric field strength E varies with distance x in the space between the two plates? In order to answer this question, it is helpful to consider the electric field acting on a small positive test charge. If we place the charge right next to the positive plate, then it will be repelled by the positive plate and attracted by the negative plate, so it will want to move from left to right. Therefore, the electric field is positive, which at the moment doesn't rule any of the four graphs out. However, we would expect that next to the positively charged plate, there is an electric field acting on the charge, because it is repelled. Therefore, what we expect is that the electric field is non-zero at the positive plate. Equally, it should be non-zero at the negative plate, because this is a positive charge being pulled towards negative charges, and therefore we expect an electric force to be non-zero there too. Since the plates are at x is equal to 0, and at x is equal to a, and B and D both have a 0 electric field at x is equal to 0 and x is equal to a, B and D must both be out. To narrow it down between A and C, we can use what we know about the field between two oppositely charged plates in a capacitor. Specifically, we know that each lot of positive charge will generate the electric field at one plate, and the lot of negative charge will generate the electric field at the other plate. The strength of the field is proportional to the size of the charge. And in a normal parallel plate capacitor, the field lines are evenly spaced. This means that the field is uniform. So that means that the electric field has to be the same. So C must be out too, because C has the electric field starting from a certain value, decreasing, and then increasing again. This means that our answer has to be A, since it's the only one which has a uniform field that's non-zero at both the plates. This question is about electric fields. The question says, a particle of mass m, charge q, and charge q is accelerated through a potential difference v over a distance d. What is the average acceleration of the particle? Because we're dealing with acceleration in relation to the electric force, it is helpful to consider Newton's second law, which says that F is equal to m times a, where F is the resultant force acting on the object, m is its mass for an object where the mass doesn't change, and a is its acceleration. From here, we need to determine what the electric force is acting on the particle. To do so, we can use that we've been told that we have a potential difference v over a distance d. This is related to the electric field by the equation E, the electric field, is equal to the potential difference divided by the distance, where we selected this equation because we have both v and d. Note that we can use this equation because the question has asked us for the average acceleration of the charge. This means that if we divide the potential difference that the charge has moved through by the distance that it's moved through, that this will give us the average value of the electric field. Where what we've done is we've replaced whatever complicated thing is going on with the electric field in full over the whole motion with an average field that looks like it's uniform the whole time, that gives the same result. This in turn will lead us to the average value of the force, which will lead us to the average value of the acceleration. Therefore, we know that we can just get the electric field by dividing these two quantities. Then, the electric force is related to the electric field by multiplying it by the charge, Q, because the electric field describes the force per unit charge exerted on a small positive test charge in the electric field. Therefore, we have that the electric force is given by Q multiplied by E. Now, substituting this in here, we find that the electric force is given by QV divided by D. We can now combine this with Newton's second law because we know that the only force acting is the electric force. And so we obtain QV divided by D is equal to the mass times by the acceleration. So therefore, we can divide by m, the mass, to obtain an expression for the acceleration given by QV divided by md. Therefore, our answer is A. This question is about electric fields. The question says, an electron moves for a distance of 0.10 meters parallel to the field lines of a uniform electric field of strength 2.0 kilonewtons per coulomb. What is the work done on the electron? In order to do this question, we need to recall the definition of the work done, where the work done is equal to the force applied multiplied by the distance moved in the direction of the force. So for an electron, what I have is that it will go in the opposite direction to the field lines, which is still parallel to the field lines. This is because the electron is negative, and so field lines show the direction that a positively charged particle experiences a force in. Therefore, the electron will experience a force in the opposite direction. The point is that work will be done on the electron in this case because it is moving parallel to the field lines. So, then we need to use the equation for work done on a charge moving for a distance d parallel to the field lines. Specifically, this equation is given by W is equal to Q times by V, where Q is the charge. Since we're dealing with electron, this is E. And we need to find an equation for V. We know that in a uniform field, we have that the electric field strength, E, is related to the potential difference and the distance that that potential difference is over. Therefore, we can rearrange this equation to have V is equal to E times by D, like so. Then we can substitute this into the equation for W. So we have that W is equal to Q multiplied by E times D. So therefore, from there, we can write W is little e times the electric field strength times by D, and then we can substitute in the numbers here. So we have that little e is 1.60 times 10 to the minus 19 coulombs. We have that the electric field is given by 2 times 10 to the 3. This is to convert kilonewtons to newtons. And the distance is given by 0.1. Therefore, we get an answer of 3.20 times 10 to the minus 17 joules, which is given by C. This question is about capacitors. The question says, a parallel plate capacitor is fully charged and then disconnected from the power supply. A dielectric is then inserted between the plates. Which row correctly identifies the charge on the plates and the electric field strength between the plates? In order to answer this question, it is helpful to consider what disconnecting the power supply does to the charge acting on the plates. Specifically, consider having charged the capacitor such that we have a positive charge on one plate and a negative charge on another, and that we connect this. Like so. Currently, there is a charge of plus Q on the left-hand plate and minus Q on the right-hand plate. Then we disconnect the power supply. So we cut out the wires that are connecting the capacitor to the cell. Then what we have is just the capacitor on its own. When the capacitor is on its own, there's nowhere for the charge to go, because it cannot flow through a circuit because there is no circuit produced. Since it is fully charged when the cell is connected, charge will also not flow off the capacitor while the power supply is being disconnected. Therefore, the charge has to remain the same. Therefore, what we can say is that it cannot be B and it cannot be C, because both of these say that the charge has increased. Now we need to consider the action of putting in the dielectric. Remember that putting in the dielectric cannot affect the charge because the charge still has nowhere to flow. In order to understand the effect of the dielectric, we consider the equation for the capacitance of the capacitor. Specifically, we have that for a parallel plate capacitor, capacitance C is equal to epsilon naught, the permittivity of free space, which is a constant, multiplied by epsilon r, the relative permittivity, multiplied by A, the area of the plates, divided by D, the separation between the plates. So the quantity that we're interested in here is epsilon r, the relative permittivity. The relative permittivity describes how difficult it is to set up an electric field with a certain amount of charge. Specifically, larger relative permittivity means that you get a smaller electric field between the plates for the same amount of charge. To see this, we can consider how this equation for C affects the voltage with a certain amount of charge. So we know that the charge stays the same, so we can now use the equation Q is equal to C times V. Now, if the relative permittivity increases, because the dielectric will have a higher permittivity than free space, then it means that C must increase, but Q is constant, which means that V must decrease, because if C is a larger number, then V must be a smaller number for the two to multiply to still get the same value of Q. We've come to this conclusion because epsilon r is directly proportional to C, the capacitance. Therefore, what we see is that the potential difference across the plates decreases. Now, since we have that the potential difference, V, is equal to E times by D, or this comes from the electric field is equal to the potential difference divided by the distance between the plates, what we see then is that for a smaller value of V, and the plates at the same distance apart from each other as before, we have a smaller value of the electric field strength. Therefore, the answer has to be D. This question is about capacitors. The question says, a capacitor of capacitance C has a charge of Q stored on the plates. The potential difference between the plates is doubled. What is the change in the energy stored by the capacitor? In order to answer this question, it is convenient to consider the energy stored in the capacitor in equation form. Specifically, that if I store a charge Q on the capacitor, potential difference V, the work done putting those charges on the capacitor at that potential difference is given by a half times Q times V. Since whenever the potential difference is changed, it is also likely that the charge is going to change in this case on the plates, it is helpful to consider rewriting this equation in terms of the capacitance, a quantity which will not change. To do so, we can use the equation C is equal to Q over V and rearrange for Q or V respectively. So that gives us either Q is equal to CV or V is equal to Q divided by C. If we substitute in W, then we get that W is equal to a half times by, in this case, C times V squared. So we put in Q into the W equation, or over here, we can substitute in for V instead, and we get a half times Q squared divided by C. So this is convenient to write like this, because this way we keep the equation for W in terms of only one quantity which is changing, V or Q in each case. The energy originally stored in the capacitor then is best written using the equation W is equal to a half times by CV squared, because we're about to change the potential difference. If we then take V becomes 2 times itself, the new energy is equal to W new, which is equal to a half times C times by 2V all squared, which is equal to 2CV squared. Therefore, we can write the change in energy stored as the second value subtracting the first value. So this is W new minus W, and that's just equal to 2CV squared minus a half CV squared, which is 3 over 2CV squared. So note that this question has asked us for the change, which you have to be careful to do. Next then, we need to turn this back into the equation for charge, because that's what the answers are in terms of. So here we use again that Q is equal to CV. And so from doing that, V is equal to Q over C. And so we have that the change in energy is given by 3 over 2 times by C, and then substituting in this equation for V, we find that it's Q divided by C again, all squared, which gives us 3 over 2 Q squared divided by C. This means that our change in energy is 3Q squared divided by C, and so that means that our answer is C. This question is about capacitors. The question says, a capacitor consists of 2 parallel square plates of side L separated by distance D. The capacitance of the arrangement is C. What is the capacitance of a capacitor with square plates of side 2L separated by a distance D divided by 2? In order to answer this question, it is helpful to consider an equation that gives the capacitance in terms of the geometric properties of the capacitor, specifically that the capacitance is equal to epsilon naught, the permittivity of free space, which is a constant, multiplied by epsilon r, the relative permittivity of the material within the capacitor, which in this case we don't need to worry about, the area of the two plates, and the distance separating the plates. We selected this equation because we have been told about the various physical properties of the capacitor, the distance between the plates, and the side length of the plates, which will be related to the area, in contrast to something about the voltage across the capacitor or the charge stored on it, in which case we would select a different equation. So in this case, because we have square plates of side L, their area is equal to L squared, because we just have an arrangement that looks like this. So therefore we can rewrite our equation for the capacitance C as epsilon naught epsilon r multiplied by L squared divided by D. So note here that what we have is that if the area increases, then so too does the capacitance. And if the distance between the plates increases, then the capacitance decreases. This is because it is possible to store more charge on a plate of larger area, which means that more charge per unit volt can be stored. Also, that separating the plates by a larger difference means that you can set up a smaller potential difference per unit length. Anyway, with this in hand, we can now calculate the new capacitance, C nu. So using the same equation as before, we have epsilon naught r multiplied by A divided by the new distance, D divided by 2. Now, we know that A here, or A nu to be completely precise, is equal to 2L squared, because this is still a square set of plates. So we have that C nu is epsilon naught epsilon r multiplied by 4L squared divided by D divided by 2. So C nu is equal to 8 epsilon naught epsilon r times by L squared divided by D. But this factor here is just the old C. So this is equal to 8 times C. Therefore, because we've determined that C nu is equal to 8C, our answer has to be D. This question is about capacitors. The question says, a capacitor of capacitance 120 microfarads is charged and then discharged for a 20 kiloohm resistor. What fraction of the original charge remains on the capacitor 4.8 seconds after the discharge begins? In order to answer this question, we should use the fact that the capacitor is discharging. This means that we can apply the equation for the decay of charge in the capacitor as Q is equal to Q0, the initial charge, multiplied by e to the minus t divided by RC, where e is Euler's number, approximately 2.718, t is the time elapsed since the capacitor began discharging, and R is the resistance of the resistor that the capacitor is discharging through, and C is its capacitance. This will have units of time. We selected this equation because we're interested in the decay of charge on the capacitor over time, which this equation includes. So, in order to do this then, we can rewrite this equation by dividing by Q0, as Q divided by Q0 is e to the minus t divided by RC. So in this question, we're interested in determining what this fraction of charge is, Q divided by Q0. In the question, we've been given the time at which we want to evaluate this. We've been given the resistance of the resistor that it discharges through, and we've been given the capacitance C. So we can calculate this, and first we'll do RC, which is given by 20 times 10 to the 3 from the resistor. So this is from converting kiloohms to ohms. And then from the capacitance, we've got 120 times by 10 to the minus 6. So that comes from converting microfarads into farads. So RC then is given by 2.4 seconds. So then we can evaluate t divided by RC, which is equal to 4.8 divided by 2.4, which is 2. Therefore, we have that Q divided by Q0 at this particular time, 4.8 seconds, is given by e to the minus 2, which is 0.1353 ... which is approximately 0.14 to two significant figures. This means that Q divided by Q0 is equal to 0.14, and so our answer has to be A. This question is about Faraday's law. The question says, a coil with 20 circular turns, each of diameter 60 millimeters, is placed in a uniform magnetic field of flux density 90 milliteslas. Initially, the plane of the coil is perpendicular to the magnetic field lines, as shown in figure X. The coil is rotated about a vertical axis by 90 degrees in a time of 0.20 seconds, so that its plane becomes parallel to the field lines as shown in figure Y. Assume that the rate of change of flux linkage remains constant. What is the EMF induced in the coil? In this question, since we are dealing with an induced EMF, it is helpful to consider the equation for an induced EMF in terms of the rate of change of magnetic flux linkage, specifically that the induced EMF is equal to the rate of change of the magnetic flux linkage n times by phi, where n is the number of turns in the coil, in this case 20, and phi is the magnetic flux. Since we have been told that the rate of change of flux linkage remains constant, we can approximate this by taking the difference between the magnetic flux at the end and the start, and then dividing it by the change in the time. So this is the rate of change of the magnetic flux, delta phi, divided by delta t. So epsilon is given by n multiplied by this quantity. Now, what we know is that t end minus t start, which is delta t, is just given by 0.2, because that's the total time that it takes for the coil to rotate. To make progress, we need to consider the equation for the magnetic flux, specifically that phi is equal to the size of the magnetic flux density multiplied by the area it moves through multiplied by cosine of an angle theta. The angle theta is the angle between the normal to the area and the direction of the magnetic flux density. What this means is that because the normal to the area in figure X is going outwards, like so, then theta in this case is equal to 0 degrees, because the normal is parallel to B. However, in this case, in figure Y, the normal is coming out of the screen. Therefore, there's a right angle between the magnetic flux density and the normal from the area. Therefore, here, theta is equal to 90 degrees. The other two quantities remain the same. The magnetic flux density hasn't changed, and the area of the coil itself hasn't changed. Therefore, the only thing that has changed is cosine of theta. And this has gone from 1 to 0. Since cosine of 0 degrees is 1, and cosine of 90 degrees is 0. Next, we need to work out the area of the coil. Specifically, we have the diameter, d, and so we can relate this to the area, since this is a circle, as pi multiplied by r squared, which is equal to pi multiplied by d, the diameter, divided by 2 squared, where the radius is just the diameter divided by 2. Therefore, we expect the area to be pi times by 60 divided by 2 times by 10 to the minus 3 squared, where we've done this to convert millimeters to meters, so we can use our equation in normal SI units. So with all this in hand, we know that phi end, because cos theta is equal to 0 and phi is proportional to cos theta, we know that phi end is equal to 0. So what that means then is that to calculate epsilon, we do epsilon is equal to n, which is 20, multiplied by minus phi start, where phi start is just given by b times a. So that's equal to pi times by 60 divided by 2 times 10 to the minus 3, all squared, times by the value of the magnetic flux density, which is 90, times by 10 to the minus 3, and that's to convert milliteslas to teslas, so we can use SI units as normal. And then we can use that the time difference, delta t, is 0.2. Therefore, we calculate that epsilon is equal to 0.0 or minus 0.02544, which is equal to minus 25 millivolts. However, one thing we have to be careful with using this equation as is above, epsilon is delta n phi divided by delta t, is that this equation strictly gave us the magnitude of the EMF, which cannot be negative. Therefore, we have to make sure to take the positive value of this. So in other words, we have to say that the magnitude of epsilon is equal to 25 millivolts. Note that if we had included a minus sign here, as per Lenz's law, then these two minus signs would have cancelled out anyway to get us 25 regardless. But in this case, we just use the equation for the magnitude of the EMF, as is provided on the datasheet. Anyway, since we calculated that the magnitude of epsilon is 25 millivolts, it means that the answer to our question is C. This question is about mean power. The question says, the mean power dissipated in a resistor is 47.5 microwatts, where the root mean squared voltage across the resistor is 150 millivolts. What is the peak current in the resistor? In order to answer this question, it is helpful to consider the equation for the mean power dissipated, specifically that P, the mean power, is equal to the RMS current, IRMS, multiplied by the RMS voltage, VRMS. This equation is frequently used because in a circuit with an alternating current, the power dissipated across the resistor will be changing. VRMS and IRMS represent the root mean squared value of the voltage and current, so give the mean power dissipated within the resistor. However, we now wish to relate the RMS current to the peak current, which we can do with the equation from the datasheet. IRMS is equal to I0, which is the peak current, divided by the square root of 2. Therefore, we can rewrite this equation as P is equal to I0 divided by square root of 2 multiplied by VRMS. We did this because we've been given VRMS in the question, and we've also been given the mean power, and we wish to find the peak current. We can then rearrange this equation for the peak current by multiplying both sides by the square root of 2 and dividing by the root mean square voltage, like so. This leaves us with the square root of 2 multiplied by 47.5 times 10 to the minus 6 That's from converting microwatts to watts, and the micro has the power of 10 to the minus 6, or the power of 10 of 10 to the minus 6. And then VRMS is given by 150 times 10 to the minus 3, where the 10 to the minus 3 comes from converting millivolts to volts. So the milli has an associated power of 10 to the minus 3. And this gives us a value of I0 equal to 4.4783 times 10 to the minus 4 amps, which is approximately equal to 4.5 times 10 to the minus 4 amps. Therefore, our answer is B. This question is about the national grid. The question says, the national grid is used to transfer electrical energy from power stations to consumers. What conditions for the transmission voltage and the transmission current give the most efficient transfer of energy through the national grid? In order to answer this question, it is useful to consider a certain output power and then look at how varying the current and the voltage affects how much of that output power is transported. What I mean by this is that we can write the equation for output power P is equal to I times V. If we take P to be fixed, then we can rearrange for I. Specifically, dividing both sides by V, we get I is P divided by V. Now we need to consider the power dissipated in the wires. We can see this by using the same equation, except we need to consider the power dissipated in wires of resistance R. So using the equation from the data sheet, this is I squared R. Substituting in our equation for I, we have that this is equal to P squared times by R divided by V squared. Therefore, we see that larger voltages give smaller power loss in the wires. This is because if V is a very big number, then the value of P squared, which is a constant, times by R, which is a constant, divided by V squared, gets smaller. Also, because I is equal to P over V, this implies that if V is made larger and P is a constant, then I also gets smaller. Therefore, the most efficient situation is when V is very large and I is small. Therefore, we can say that we can now compare it to the various options we've been given. So firstly, we require the transmission voltage to be high, so that keeps A and B, and rejects C and D because they both say low. And then we also want a small transmission current, which means that now we reject A too. Therefore, our answer is B, because this has a high transmission voltage, which will minimize the power dissipated in the wires, and through that, we have a small transmission current. This question is about transformers. The question says, a mains transformer has a primary coil of 2,500 turns and a secondary coil of 130 turns. The primary coil is connected to a main supply where VRMS is 230 volts. The secondary coil is connected to a lamp of resistance 6.0 ohms. The transformer is 100% efficient. What is the peak power dissipated in the lamp? In order to solve this, we first need to figure out what the voltage is in the secondary coil. In doing so, we will be able to use the power equation to then work out the power dissipated in the lamp. So first, the voltage across secondary coil is given by the equation NP divided by NS is equal to VP RMS divided by VS RMS, where N is a number of turns and N is a number of turns and V is a potential difference across one of the coils, and the P represents the primary coil and S represents the secondary coil. Note that we know to use this equation because we've been given the number of turns in both the primary and secondary coils, as well as the voltage across one of the coils. Rearranging, we find that Vs RMS is equal to Vp RMS multiplied by Ns divided by Np. Note that here we've been able to use the RMS values of both the primary and the secondary coil voltage. This is fine because both of them are related to their peak voltages by the same factor. We're going to use this later anyway, as for example, Vp RMS is equal to Vp 0 divided by the square root of 2. Therefore, in the expression Vp 0 over Vs 0, the factors of root 2 will cancel out to give us Vp RMS over Vs RMS. From here, we can work out the value of Vs RMS as being equal to Vp RMS, which is 230, multiplied by 130, the number of turns in the secondary coil, divided by the number of turns in the primary coil, Np. This gives us Vs RMS as 11.96 volts. From here, we should write an equation for the peak power dissipated in the lamp. Specifically, we know that the peak power is given by the peak current in the secondary coil, so I0S, multiplied by the peak voltage in the secondary coil, V0S. Then we can use Ohm's law, which says that for the lamp of resistance R, which will be 6 ohms, we have that V0S is equal to I0S multiplied by R. So this is just using Ohm's law, but with the subscripts corresponding to the peak voltage and current and in the secondary coil. So we can rearrange this for I as I0S is equal to V0S divided by R. So this gets us an equation which looks like V0S all squared divided by R. So this is our equation for the peak power dissipated in the lamp. Now we have to use our other equation, which is that Vs RMS is equal to Vs0 divided by the square root of 2, which is just saying that the mean voltage through the coil is equal to the peak voltage through the coil, which will also be through the lamp, divided by the square root of 2, as we discussed earlier for the primary coil. Therefore, what we can say is that the peak power, rearranging this to be Vs0 is equal to square root of 2 Vs RMS, is equal to 2 over R multiplied by Vs RMS, all squared. So then we can substitute in what we know for Vs RMS and for R to get 2 divided by 6 multiplied by 11.96 all squared. This gives us a value of 47.6805 ... which is approximately 48 watts. Therefore, our answer is C. This question is about Rutherford scattering. The question says, the Rutherford scattering experiment led to A. the discovery of the electron, B, the quark model of hadrons, C, the discovery of the nucleus, and D, evidence for wave-particle duality. The Rutherford scattering experiment is an experiment in which alpha particles were fired at a gold film, and then the angle at which the particles came off was investigated. In this experiment, it was found that most particles are undeflected, that some particles deflected by a small angle, and some were directed back at 180 degrees. These observations lead us to conclude that firstly, the atoms in the gold film were mostly composed of empty space. This is because most of the alpha particles went through undeflected. Secondly, the fact that some of the alpha particles were deflected at small angles relative to the direction they came in at suggests that there is a charged object at the center of the atom. This is because the alpha particles themselves are charged, and so interact with other charged objects. This is how they would be deflected. The charged nucleus pulls them towards or away from it. Without knowing what the charge on the nucleus is, it is impossible to say which of these two things would happen. This is where the final observation comes in. Specifically, that some of the alpha particles were directed back at 180 degrees, so going completely back on themselves. What this meant was that because the alpha particles are positively charged, the nucleus itself must also be positively charged to repel the alpha particles backwards. Otherwise, alpha particles that were going to collide directly with the nucleus would just be attracted closer to the nucleus, rather than being repelled and going back the direction that they came. Therefore, the positive charge in the atom must be concentrated in the center, in the nucleus. This constitutes evidence for the existence of the nucleus. Therefore, our answer is C. For interest, the discovery of the electron was done by J.J. Thomson when he experimented with cathode rays. Evidence for the quark model of hadrons comes from electron-positron pair production, where various hadronic particles are produced, and evidence for wave-particle duality comes from diffraction of matter waves, where beams of electrons can be made to be diffracted. This question is about radioactivity. The question says, a Geiger counter is placed near a radioactive source, and different materials are placed between the source and Geiger counter. The results of the tests are shown in the table. We have a table where putting different materials between the source and the detector changes the count rate. What is the radiation emitted by the source? In order to answer this question, we need to collect some facts together about the different kinds of radiation. Specifically, we're interested in how easily they are absorbed by matter. So for alpha, we have that alpha is easily absorbed. This means that it has a short range in air, and an even shorter range if something like paper is put in front of it. This is because an alpha particle has a 2+ charge and a large mass. What this means is that it is easily attracted to other forms of matter, and because of its large mass, it moves slower than the other kinds of radiation. Therefore, it's more easily absorbed. As for beta, beta is less easily absorbed, so it has a range in air of about 1 meter. What this means is that you need a slightly stronger absorber rather than something like paper to absorb beta radiation. Therefore, something like aluminium will do the trick. These properties come about because beta radiation is made up of either positrons or electrons, so E plus or minus. So what this means is that because the mass is much smaller than an alpha particle, Since this is an electron as opposed to a helium nucleus, and the charge is only plus or minus 1 times by the elementary charge, so it has a smaller charge too. Therefore, it is harder for matter to attract and absorb it, since it will be moving faster. And smaller charges are less easily attracted. Finally, we have gamma radiation, which is much less easily absorbed. This is because gamma radiation is made up of photons, high energy photons at that, and so therefore, because they have no mass and are uncharged, it's much harder for them to interact with matter. Therefore, you need very dense materials in order to increase the probability that a nucleus or other particle interacts with the gamma photons. Note that the density requirement can be substituted for a thick material. The point is that you have lots of chances for the gamma photon to interact with another particle. So things that are used to attenuate gamma radiation are things like steel or lead. Combining these facts, we can use the tests here to figure out what radiation are present in the source. So relative to the test whenever there's no material present, this is the control test, we see that for paper, there is no change in the count rate of the Geiger counter. This implies that there's no alpha. Adding the aluminium foil causes the count rate to decrease. This would serve to remove alpha radiation if it was present, which we've already determined it isn't, as well as beta radiation. Since the count rate has gone down, there is beta present in the radioactive sample. By adding thick steel, the count rate decreases from 1000 to 50. What this means then is that we've managed to remove some of the incident radiation. Since the count rate has decreased further than if the aluminium foil is added, not only has the beta radiation been removed, but also there must be gamma radiation because the count rate is even lower. Thus, we've determined that in the source there must be both beta and gamma radiation present, so the answer is D. This question is about radioactivity. The question says, nobelium-259 has a half-life of 3,500 seconds. What is the decay constant of nobelium-259? In order to answer this question, we note that we've been given the half-life, T half, and we want to find the decay constant, lambda. To do so, we should use the equation T half is equal to 1 over lambda multiplied by the natural logarithm of 2. Since this is an equation that contains lambda in terms of T half. This equation comes from the fact that for a radioactive sample with n radioactive nuclei, and we know that initially we had n0 radioactive nuclei, the two are related by n is equal to n0 times by e to the minus lambda t, where lambda is the decay constant and t is the time elapsed since we had n0 nuclei. Dividing n by n0, we find that this is equal to e to the minus lambda t. Now, whenever n over n0 is a half, that's one half-life. So we can also write this as a half to the power of t divided by t half, like so. This second half of the equation over here, a half to the t divided by t half, says that every time that the time is a multiple of the half-life, we get another power of a half. So after one half-life, n over n0 is halved. After 2, n over n0 is equal to a quarter, and so on. By doing some mathematical manipulation, this equation is rewritten in the form over here. So rearranging then, we have that lambda is equal to 1 over t half, multiplied by the natural logarithm of 2. Therefore, we can substitute in numbers for this, so lambda is equal to 1 over 3,500 multiplied by the natural logarithm of 2. This gives us lambda is equal to 1.980 ... times 10 to the minus 4. And this is in units per second. Therefore, this is approximately 2.0 times 10 to the minus 4 per second to two significant figures. Therefore, our answer is B. This question is about activity. The question says, a pure sample of nuclide X containing n nuclei has an activity A. The half-life of X is 6,000 years. A pure sample of nuclide Y containing 3n nuclei has an activity of 6A. What is the half-life of nuclide Y? To solve this question, firstly, we are told that a nuclide X with n nuclei has activity A. We can write an equation that relates the activity A to the number of nuclei n, which comes from the datasheet as A is equal to lambda n. I'm going to give lambda the subscript x to show that we're talking about nuclide X here. Secondly, we also know that we're interested in the half-life. So we need to find an equation on the datasheet that involves the half-life that can relate to the decay constant. Such an equation exists in the form of t half, the half-life of x, is equal to 1 over lambda x multiplied by the natural logarithm of 2. We can use this equation either for x or for y. Therefore, we can write that t half is inversely proportional to the decay constant of the nuclide, whichever one it is. Okay, so now we can do the same thing for y to figure out what the decay constant of y should be. Specifically, we can write that the activity A of y, which is equal to 6 times the activity of x, is equal to lambda subscript y multiplied by ny. And we know that there are 3n nuclei in the sample of y. This implies that lambda y is equal to a divided by n multiplied by 2. This can be related to lambda x by noting that lambda x is just given by a divided by n. Therefore, lambda y is equal to 2 times lambda x. Then, using that t half is inversely proportional to lambda, what we find is that because lambda y is equal to 2 times lambda x, it means that t half y must be equal to a half times by t half x. This is because since t half is inversely proportional to lambda, an increase in lambda by factor 2 means that t half must decrease by factor 2. Therefore, our answer is equal to the half-life of x divided by 2. This means that t half y is equal to 6,000 divided by 2, which is equal to 3,000 in years. Therefore, this is equal to B. This question is about activity. The question says, cobalt-60 has a half-life of 5.27 years. What is the total activity of 1.0 grams of cobalt-60? In order to answer this question, we should use the definition of activity, which is that A, the activity, is equal to lambda, the decay constant, multiplied by n, the number of nuclei in the sample that are radioactive. In order to make progress, we need to determine lambda and n from the data we've been given. Firstly, we know that we've been given the half-life, t half, so we need an equation that relates t half to lambda. One such equation is t half is equal to 1 over lambda multiplied by the natural logarithm of 2. Therefore, we can rewrite this as lambda is equal to 1 over t half multiplied by the natural logarithm of 2 by multiplying both sides by lambda and dividing both sides by the half-life, t half. So we've got lambda, but we still need n. N is the total number of radioactive nuclei in the sample. Therefore, if we use the fact that the number of particles is equal to the total mass of the sample divided by the mass of one radioactive nucleus of cobalt-60. So in writing this equation, what we've done is that we said that our sample has to be made up of a certain number of cobalt-60 nuclei, so we can split that into a number of pieces, each which have the mass of one cobalt-60 nuclei, and therefore get the total number of particles. So substituting numbers in, what we find is that we have a total mass of 1 times 10 to the minus 3 kilograms. So this is converting grams to kilograms because the kilo includes a prefix of 10 to the 3. So converting grams to kilograms means that we must multiply by 10 to the minus 3. Then, for the mass of 1 cobalt-60, we can use that this is 60 multiplied by the atomic mass unit, because this 60 here is given as 60U. That's what cobalt-60 describes in terms of its mass. So it's 60 times by the atomic mass unit, 1.661 times 10 to the minus 27. Therefore, we get that we have 1.003411 times 10 to the 22 particles, or radioactive nuclei. So we have n. Now we need lambda. To do that, we use the equation above, which is that lambda is equal to 1 over t half multiplied by natural logarithm of 2. So substituting numbers in, we have to make sure to convert years into seconds. So it's 5.27 multiplied by 365. So this is in days in a year. Multiplied by 24. So this is hours in a day. Multiplied by 60. Multiplied by 60 again. So this is the number of seconds in an hour. This is because there are 60 minutes in an hour and 60 seconds in a minute. So doing all of those conversions, we find that lambda is equal to 4.170693 times 10 to the minus 9 per second. Therefore, we can calculate the activity A as the product of these two numbers. So A is equal to 1.003 times 10 to the 22. Remember, we should use our unrounded answers here to avoid making any rounding errors. Multiplied by 4.170693 times 10 to the minus 9, and that gets us 4.18598. Whoops. 18598 times 10 to the 13, which is approximately equal to 4.2 times 10 to the 13. And that's an activity, so it's in units of becquerels. Therefore, our answer is A. This question is about the nuclear radius. The question says, the radius of a nucleus of the iron nuclide 5627 iron is 4.35 times 10 to the minus 15 meters. What is the radius of a nucleus of the uranium nuclide 23892 uranium? In order to answer this question, we need to consider an equation that contains the nuclear radius of a nuclide. A relevant equation is given by R is equal to R naught multiplied by a to the third, where a is the nucleon number, which in this case is 56, and 238, and which I've labelled A subscript Fe for iron and A subscript U for uranium, respectively. And R naught is some standard radius, which is usually 1.2 femtometers. However, we're not given that in this question, and so can't use it. In order to make progress, we need to use the fact that we've been given 2 nuclides rather than 1. Specifically, we already know that for an iron nuclide with a nucleon number of 56, the radius is given by 4.35 times 10 to the minus 15. Therefore, we should use the fact that R is proportional to A to the 1 over 3. To use this idea, we need to write an equation for each of RFE, the radius of the iron nuclide, in terms of AFE, like so, and the same for uranium. Then, to make progress, we see that the constant R0 is in both equations, so if we divide one by the other, then we can come up with an equation that does not contain it. Specifically, if we do this, Ru divided by Rfe, we get R0 A U to the power of a third divided by R0 A subscript Fe to the power of a third. What this means then is that R0 cancels since it is present on both the top and the bottom. Therefore, we have that Ru over Rfe is equal to Au divided by Afe to the power of a third. Therefore, we can write an equation for Ru in terms of the other 3 variables that we know. Specifically, Ru is equal to Rfe, which we're given, multiplied by Au divided by Afe to the power of a third. Substituting numbers in then, we find that this is equal to 4.35 times 10 to the minus 15. So taking Rfe from up here as the radius of the iron nuclide, multiplied by the nucleon number of the uranium nucleus, divided by the nucleon number of the iron nucleus to the power of a third. So that gives us 238, and then 50 divided by 56 to the power of a third. This gives us a value of 7.046 times 10 to the minus 15. And so Ru is approximately equal to 7.05 times 10 to the minus 15 meters. This is to 3 significant figures because the data in the question has all been given to 3 significant figures where appropriate. Therefore, our answer has to be D. Note that this is a sensible answer to obtain because 7.05 times 10 to the minus 15 meters is still around a similar size to the size of an iron nuclide. We don't expect the nuclei to get much bigger than each other since we've only added about 180 more nucleons. This question is about binding energy and fission. The question says, uranium-236 undergoes nuclear fission to produce barium-144, krypton-89, and 3 free neutrons. What is the energy released in this process? In order to answer this question, we need to consider the concept of binding energy. Specifically, the binding energy is the energy that the nucleus gives out by bringing all the nucleons together to form the nucleus. So, in this process of the nucleons coming together, energy is given out. In this question, we're given the binding energy per nucleon. So therefore, any binding energies that we want to calculate are going to result from multiplying the binding energy per nucleon by the number of nucleons in that nuclide. So in order to save on the writing, I'm going to write the binding energy of uranium as B subscript U, the binding energy of the barium as B subscript B, and the binding energy of the krypton as B subscript K. The energy released is going to be the difference between the two energies in this process. Specifically, the energy released will be the energy after subtracted by the energy before. As we'll see, this energy difference arises because the nucleons in the barium and krypton nuclei form a more stable configuration and therefore give out more energy whenever they bind than in the uranium nuclide. This is reflected in the fact that the barium and krypton nuclei have higher binding energies per nucleon than the uranium. In order to do this then, we want to write expressions for the energy after and the energy before. So firstly, for the energy after, we can use the fact that we have 144 nucleons in the barium nucleus, which gives us 8.3, which is BB, times by 144. And then in the krypton nucleus, we have 89 nucleons. So we have 89 times by BK, which will be 8.6. And we also have a contribution due to the energy that comes from the mass of each of the nucleons. We'll deal with this in a second after we've written the expression for E before. In the same way, E before is given by Bu, the binding energy of one uranium nucleon, multiplied by the number of nucleons in the uranium nucleus, which is times 236. So therefore, Bu times 236 is our energy before, in addition to the energy that comes from the mass of the nucleons. I've written that E mass is the same in both of these equations, so we need to consider why that is to proceed. Specifically, the energy that comes from E mass, which is the energy corresponding to the mass of all the protons and neutrons on both sides of the equation, we can add up the total number of protons and neutrons on both sides first. So before, we have 236 nucleons, which leads us to 92 protons, and also to 236 minus 92 neutrons. So that's 234, and then that leads us to 144 neutrons. The reason that this is true is because the number 92 is the atomic number and tells you how many protons. The number 236 is the mass number, which tells you the total number of nucleons. So subtracting 92 from 236, the number of protons from the total number of nucleons, we get the number of neutrons. We can do the same calculation for after, and we find that we have 56 plus 36 protons, which is equal to 92. And we find that we have 144 minus 56 from the barium, plus 89 minus 36 from the krypton, for the exact same reason as before when we were calculating the number of neutrons in the nucleus, plus 3, because we have free neutrons. So that gives us 144 neutrons again. So the energy E mass in each case is calculated by the number of protons times by the proton mass, MP, plus the number of neutrons multiplied by the neutron mass, Mn. Therefore, E mass is the same in both situations, before and after. Therefore, we can calculate delta E is equal to 144 times by BB, which I'll substitute in as 8.3, plus 89 times by BK, which is 8.6, plus E mass, minus the binding energy of uranium per nucleon, which is 7.5, times by 236. And then that's also subtracting E mass, because we subtract both of the quantities in the energy before. So this is the same as putting brackets around this and pulling out a minus sign. So therefore, we see that E mass cancels with itself, because there's one add of E mass and one subtraction of E mass. So we're left with delta E is equal to 190.6. And these values have all been in mega electron volts. Therefore, our answer has to be C.